Hello there and welcome to Science for Sleep, where curiosity gets comfortable, science slows down a little, and tonight's journey takes us somewhere very few people ever think to look. Not out toward a distant galaxy, not toward a newly discovered planet, not even toward one of the black holes that seem determined to steal all the attention these days. Instead, we're going to spend some time exploring something enormous that has been quietly surrounding our own galaxy this entire time, and the strange part is that we didn't even know it was there until quite recently. Imagine for a moment that you lived in a house your entire life. You knew every room, you knew where the doors were, you knew where the windows were, you knew every creaky floorboard and every corner of every hallway. Then one day, someone points out that attached to the roof are two gigantic structures, each thousands of times larger than the house itself. Somehow nobody noticed them. That sounds ridiculous. Yet something surprisingly similar happened in astronomy. For decades, scientists studied the Milky Way in incredible detail. They mapped stars, they catalogued gas clouds, they tracked the movements of planets, they observed exploding stars and mysterious radio signals. They peered toward the centre of our galaxy and examined its outskirts. And still, hidden in plain sight, there were two colossal structures stretching far above and below the Milky Way. Structures so large that if they were visible to human eyes, they would dominate the sky. Tonight, we're going to talk about those structures, the enormous formations known as the Fermi Bubbles. Before we begin though, I'd love to know where in the world you're listening from tonight. Are you tucked into bed after a long day, relaxing on a sofa, listening through headphones during a quiet evening walk? And what time is it where you are right now? It's a fitting question because while we're sitting comfortably here discussing a discovery made only recently, the events that created these giant bubbles may have happened millions of years ago. In a way, we're about to become cosmic archaeologists. We'll be examining clues left behind long before humans existed, long before our ancestors learned to build cities, long before anyone looked up at the night sky and wondered what those stars might be. If you find this journey relaxing, interesting, or simply a pleasant way to unwind before sleep, I'd be very grateful if you gave the video a like and perhaps subscribed as well. It helps this little corner of calm science reach other curious listeners who might enjoy drifting off while learning something new. Now then, get comfortable. Settle into your chair, your bed, or wherever you happen to be. Let your thoughts slow down, and together, let's take a look at one of the strangest discoveries ever made in our own galaxy. One thing that often surprises people about astronomy is how difficult it is to study the place where we live. At first glance, that sounds backwards. Surely it should be easier to study your own galaxy than a distant one. After all, we're inside it. Shouldn't that give us the best possible view? Oddly enough, the opposite is true. Imagine standing in the middle of a forest. Trees surround you in every direction. Some are nearby, others are farther away, some are hidden behind other trees. From your position inside the forest, it can be surprisingly difficult to determine the overall shape of the woodland. Now imagine flying thousands of meters above it. Suddenly everything becomes obvious. You can see the edges, you can see clearings, you can see rivers running through it. The entire structure becomes easier to understand. Living inside the Milky Way presents astronomers with a similar challenge. We occupy a position within one of the spiral arms. We're not at the centre. We're not near the edge. We're simply somewhere within the vast disk. As a result, much of our view is blocked by gas, dust, and countless stars. Trying to understand the overall structure of the Milky Way is a little like trying to draw a map of a city while standing in the middle of one crowded street. You can gather information, you can make measurements, you can piece together clues, but obtaining the complete picture takes enormous effort. This challenge becomes even greater when the thing you're trying to find doesn't emit visible light. The Fermi bubbles are not giant glowing balloons floating in space. You can't step outside on a clear night and point to them. If you could somehow see gamma rays with your eyes, the universe would look very different indeed. Possibly alarming. Fortunately for peaceful evenings, our eyes don't work that way. For most of human history, These bubbles were completely invisible. Even after telescopes became powerful enough to reveal distant galaxies and nebulae, the bubbles remained hidden. They weren't hiding because they were small, far from it. They were hiding because they were producing a form of radiation that required specialized instruments to detect. This brings us to an interesting thought. Throughout history, every time humanity has developed a new way of observing the universe, we've discovered something unexpected. When we learned to observe radio waves, the sky suddenly filled with strange signals. When we learned to observe X-rays, violent phenomena appeared everywhere. When we learned to detect infrared light, entire regions hidden behind dust became visible. Again and again, the universe turned out to be more complicated than we imagined. It's almost as though reality enjoys keeping secrets until we've built the proper tools. In 2008, NASA launched a spacecraft known as the Fermi Gamma Ray Space Telescope. Its mission was straightforward. Study the universe in gamma rays. Now, gamma rays are the most energetic form of electromagnetic radiation. If visible light is the gentle, everyday language of stars, gamma rays are the universe shouting. They are produced by some of the most energetic events known: exploding stars, colliding particles, extreme magnetic fields, matter falling toward black holes, places where nature stops being subtle. For years, the telescope collected data, vast amounts of data. Every observation added another piece to an increasingly detailed map of the gamma-ray sky. Then something unexpected appeared. Astronomers noticed enormous structures extending above and below the centre of the Milky Way. At first glance, they looked almost symmetrical. One stretched north of the galactic centre, the other stretched south. Together they formed a gigantic hourglass-like shape, or perhaps two bubbles attached to the galaxy, hence the name, the Fermi Bubbles. Discoveries in science are often portrayed as dramatic moments. A scientist stares at a screen, music swells, someone gasps, everything changes instantly. Reality is usually less cinematic. Scientists tend to spend considerable time checking whether they've made a mistake, then checking again, then asking colleagues to check, then checking one more time just to be safe. Extraordinary discoveries require extraordinary caution. The bigger the claim, the stronger the evidence must be. And this claim was certainly big. These weren't small features. They weren't tiny anomalies hiding inside complicated data. They were gigantic. The question wasn't merely what they were, the question was how nobody had noticed them before. As more observations accumulated, the structures became impossible to ignore. The evidence kept growing stronger. The bubbles were real. Something enormous existed above and below the Milky Way's centre. Something energetic. Something powerful. Something that had apparently affected a huge portion of our galaxy. Naturally, astronomers immediately wanted answers. What created them? How old were they? Were they still expanding? Had they formed recently or millions of years ago? Most importantly, what kind of event could generate structures of such staggering size? Whenever scientists encounter something mysterious, one of the first things they do is estimate scale. Scale provides clues, and in the case of the Fermi Bubbles, the scale was almost difficult to comprehend. The bubbles extend roughly 25,000 light-years above and below the galactic centre. Think about that for a moment. A light-year is the distance light travels in 1 year. Light moves at approximately 300,000 kilometers per second. Even at that incredible speed, it requires 25,000 years to cross one bubble from base to top. Human civilization is tiny compared with those numbers. Recorded history occupies only a small fraction of that time span. The pyramids, the Roman Empire, the invention of printing, modern science, spaceflight, computers, the internet, all of it fits comfortably inside the time required for light to travel across one of these structures. And there are two of them. Sometimes astronomy forces us to confront scales that simply refuse to fit comfortably inside the human imagination. Our brains evolved to estimate distances measured in meters and kilometers, not tens of thousands of light years, Not structures spanning enormous fractions of a galaxy, yet there they are, quietly surrounding us, invisible but real. It's also worth remembering that we are living inside this system. The Fermi Bubbles are not distant objects observed through a telescope. They are part of our galactic environment. We happen to occupy a location within the same galaxy that produced them. That realization adds a certain curiosity to the story. For most of human history, we imagined ourselves learning about increasingly distant places. Instead, this discovery reminded us that our own cosmic neighborhood still contains surprises. We often assume nearby things should be well understood, but nature doesn't operate according to our assumptions. Sometimes the biggest mysteries are surprisingly close. As astronomers continued studying the bubbles, another realization emerged. Whatever created them must have released an astonishing amount of energy. The structures weren't merely large, they were energetic, filled with particles moving at extraordinary speeds, glowing in gamma rays, remaining visible across immense distances. This immediately narrowed the list of possible explanations. Ordinary events wouldn't suffice. The culprit had to be something powerful enough to influence a significant portion of the Milky Way, something capable of reshaping its surroundings on a galactic scale, and that realization pointed scientists toward one location in particular, the center of our galaxy. Because buried there, hidden behind clouds of dust and countless stars, sits one of the most remarkable objects in the Milky Way, an object that spends most of its time appearing surprisingly quiet, an object so massive that millions of suns could fit inside it, an object that may have experienced a far more dramatic past than anyone once suspected. Something curious happens in astronomy every so often. Scientists build a new instrument, point it toward the sky, and fully expect to answer a few existing questions. Instead, the universe responds by creating entirely new ones. The discovery of the Fermi Bubbles was one of those moments. Astronomers were not searching for giant structures above and below the Milky Way. That wasn't the goal. Nobody had spent decades predicting their existence. There wasn't a famous debate about them. No scientist was standing in front of a whiteboard saying, "I have a feeling our galaxy is secretly blowing enormous bubbles into space." The discovery arrived almost by accident, and that makes the story even more fascinating. To understand how surprising it was, it helps to think about what astronomers expected to see when they looked at the gamma-ray universe. By the early 2000s, researchers already knew that the sky looked very different depending on the type of light being observed. Visible light reveals stars. Infrared light exposes cooler objects and regions hidden behind dust. Radio waves uncover enormous clouds of gas. X-rays highlight some of the hottest and most violent places in existence. Gamma rays, however, belong in a category of their own. They represent the highest energy form of light known. Gamma rays are produced in environments where particles are accelerated to incredible speeds. Supernova explosions generate them. Neutron stars generate them. Black holes generate them. Entire galaxies can generate them. In a sense, gamma rays act like cosmic warning signs. When you see them, something energetic is usually happening nearby. This is why NASA launched the Fermi Gamma Ray Space Telescope in 2008. The mission carried instruments specifically designed to map the universe in gamma rays with unprecedented sensitivity. Astronomers hope to learn more about distant galaxies, pulsars, black holes, and perhaps even dark matter. The telescope was expected to answer questions. What happened instead was that it uncovered a mystery hiding inside our own galaxy. The irony is almost amusing. Scientists were looking outward. The surprise was sitting right at home. As data began flowing back from the spacecraft, researchers started assembling increasingly detailed maps of the gamma-ray sky. This was not a quick process. Astronomy rarely is. Observations accumulate gradually. Patterns emerge slowly. Months of measurements become years of measurements. Tiny signals strengthen as more information is collected. At first glance, the Milky Way looked much as expected. The galactic disk glowed brightly. Various known sources appeared exactly where astronomers anticipated finding them. There were pulsars, there were supernova remnants, there were regions where cosmic rays interacted with interstellar gas. Everything seemed reasonably normal. Then scientists began subtracting known sources from the data. This is a common practice in astronomy. Imagine trying to hear a faint sound inside a crowded room. You first identify the loudest noises, you account for them, you remove them mentally. Only then can you focus on the quieter sounds hiding underneath. Astronomers do something similar with observations. Known sources are modelled mathematically. Expected emissions are calculated. Background signals are removed. Once that process is complete, any remaining features become easier to identify, and that is when something unusual started appearing. There seemed to be excess gamma-ray emission extending upward from the galactic centre. At first, nobody jumped to conclusions. Science tends to reward caution. Unexpected signals frequently turn out to be errors. Sometimes instruments behave unexpectedly. Sometimes data processing introduces artifacts. Sometimes assumptions inside computer models prove incorrect. Astronomers have learned through experience that extraordinary discoveries often begin with attempts to prove themselves wrong. So researchers examined the anomaly carefully. Could it be a calibration issue? Could it be contamination from another source? Could it be a flaw in the model used to remove background emissions? Each possibility had to be investigated. The signal persisted. More data arrived. The structure became clearer. Then something even stranger emerged. There wasn't just one structure. There were two. One extended above the galactic centre. Another extended below it. They appeared remarkably symmetrical. That symmetry immediately attracted attention. Nature can certainly produce irregular shapes. Many astronomical objects are messy. Gas clouds twist unpredictably. Supernova remnants can appear distorted. Galaxies themselves often have unusual structures. Yet these newly observed features displayed an almost startling level of organisation. It looked as though something at the centre of the Milky Way had launched energy in both directions. North and south, up and down. Like a cosmic event that had left matching fingerprints on either side of the galaxy. The more scientists examined the evidence, the more difficult it became to explain away. By 2010, a team led by astronomer Douglas Finkbeiner formally announced the discovery. The structures quickly became known as the Fermi Bubbles. The name itself sounds surprisingly gentle. Bubbles brings to mind soap, bathtubs, and children playing outside on a sunny afternoon. The actual structures are somewhat less modest. Each bubble stretches roughly 25,000 light-years from the galactic centre. Together they occupy a region spanning around half the diameter of the Milky Way itself. If they emitted visible light, they would dominate the sky. In fact, they would be among the largest features visible from Earth. Fortunately for nighttime stargazers, gamma rays remain invisible to human eyes. Otherwise the night sky might look considerably more dramatic. One reason the discovery generated so much excitement was because the bubbles appeared surprisingly sharp. This detail often gets overlooked. Many large astronomical structures have fuzzy boundaries. Gas gradually thins out. Radiation fades smoothly. Edges become difficult to define. The Fermi bubbles seemed different. Their outlines appeared relatively distinct, almost as though some enormous event had inflated them and left behind clear boundaries. That observation raised even more questions. What kind of event creates such neat edges? How long ago did it happen? Why are the bubbles still visible? And perhaps most importantly, what does their existence reveal about the history of our galaxy? Astronomers suddenly found themselves looking at evidence of something enormous that had occurred in the Milky Way's past. The challenge was figuring out exactly what that something had been. One possibility immediately came to mind. Whenever scientists discover gigantic energetic structures near a galactic centre, they tend to think about black holes. For good reason. supermassive black holes are among the most powerful objects in existence. Despite their reputation for simply swallowing things, black holes can also launch tremendous amounts of energy. Matter falling toward a black hole doesn't disappear instantly. Before crossing the event horizon, it often forms a swirling disk. As material accelerates and heats up, enormous quantities of energy can be released. In some galaxies, this process creates jets extending thousands or even millions of light years into space. The question naturally emerged, could something similar have happened in the Milky Way? Today, our galaxy's central black hole appears relatively quiet. Compared to the active monsters found in some distant galaxies, Sagittarius A star seems almost sleepy. It isn't consuming vast quantities of matter. It isn't producing gigantic visible jets. It isn't flooding the galaxy with extreme radiation. But appearances can be deceptive. A calm black hole today does not guarantee a calm black hole millions of years ago. The Fermi Bubbles hinted that the centre of our galaxy may once have been far more active than it appears now. Of course, astronomers couldn't simply assume a black hole was responsible. Alternative explanations existed. Perhaps intense star formation near the galactic centre had generated powerful winds. Perhaps clusters of supernova explosions had collectively driven enormous amounts of material outward. After all, stars can be surprisingly influential when they work together. One exploding star releases extraordinary energy. Thousands or millions of massive stars can reshape entire regions of a galaxy. As a result, researchers found themselves examining competing possibilities. The investigation began to resemble cosmic detective work. The bubbles were evidence, the culprit remained unknown, and unlike detectives solving ordinary crimes, astronomers couldn't interview witnesses. The event responsible had happened millions of years ago. Any direct evidence was long gone. Only the aftermath remained. Imagine arriving at the scene of a volcanic eruption millions of years after it occurred. The lava has cooled. The smoke has vanished. The eruption itself is ancient history, yet the landscape still bears scars. Scientists reconstruct the story by studying those scars. The Fermi Bubbles presented a similar challenge. Astronomers were studying consequences. The cause had to be inferred. This process required observations across multiple wavelengths. Gamma rays alone couldn't tell the whole story. Researchers began comparing Fermi data with X-ray observations. They examined radio emissions. They looked for evidence of hot gas. They searched for signs of shock waves. Each data set added another clue. Gradually, a more complete picture started emerging. The bubbles appeared to contain highly energetic particles. Their structure suggested some kind of outflow from the galactic centre. The estimated energy involved was immense. Depending on the model used, the event responsible may have released energy equivalent to millions of supernova explosions. Pause for a moment and consider that scale. A single supernova briefly outshines entire galaxies. It represents one of nature's most violent events. Now imagine millions of them. Not necessarily occurring simultaneously, but producing a comparable total amount of energy. Whatever created the Fermi Bubbles was not an ordinary galactic occurrence. It belonged firmly in the category of extraordinary. The discovery also changed how scientists viewed the Milky Way itself. For a long time, our galaxy had seemed relatively peaceful, certainly not boring. There are black holes, exploding stars, and plenty of fascinating phenomena. Yet compared with some active galaxies observed across the universe, the Milky Way looked fairly restrained. The Fermi Bubbles challenged that perception. They suggested our galaxy might have experienced periods of dramatic activity. Perhaps the Milky Way's quiet appearance today represents only a temporary state. Perhaps galaxies go through active phases and calm phases. Perhaps our own galaxy has a more turbulent history than we once imagined. These possibilities transformed the bubbles from a curious discovery into something far more important. They weren't simply large structures, they were historical records, evidence preserved across tens of thousands of light years, a fossilized memory of an ancient event, and because the structures are so large, they survive for millions of years. The galaxy itself has effectively stored the evidence for us. All we needed was the technology to notice it. There is something wonderfully humbling about that. For countless generations, humans looked toward the night sky without realizing these enormous structures existed. Ancient astronomers never knew about them. Galileo never knew about them. Newton never knew about them. Einstein never knew about them. Not because the bubbles weren't there. They were. The necessary tools simply hadn't been invented yet. That realization serves as a reminder that every generation sees only part of the universe. Future astronomers will almost certainly discover things that remain invisible to us today. They will possess instruments we cannot yet imagine. They will detect phenomena we have never considered. And perhaps they will look back on our current understanding the way we look back on early maps of the world. Impressive for their time, incomplete by necessity. The discovery of the Fermi Bubbles fits neatly into that tradition. A reminder that even our own galaxy still contains surprises. A reminder that enormous structures can remain hidden in plain sight. And perhaps most importantly, a reminder that every answer in astronomy tends to generate several new questions. Finding the bubbles was only the beginning. Once astronomers knew they existed, a much bigger challenge emerged. They needed to determine their true size, their composition, their age, and the mechanism that created them. Because discovering a mystery is one thing, understanding it is something else entirely. At first glance, studying the Milky Way should be the easiest job in astronomy. After all, this is our galaxy. We live here. Every star you can see with your eyes on a clear night belongs to it. The sun belongs to it. Earth belongs to it. Every human who has ever existed has spent their entire life inside it. Surely that should make it easier to understand than galaxies located millions of light years away. Strangely enough, the opposite is often true. Some of the most detailed pictures we have of galaxies come from systems so distant that their light began travelling toward us before humans learned agriculture. Meanwhile, understanding the overall structure of our own galactic home remains surprisingly difficult. The reason comes down to perspective. Imagine standing inside a vast forest. Trees surround you in every direction. Some stand close by, others disappear into the distance. Your view is blocked by trunks, branches, leaves, and undergrowth. You can learn a great deal about the forest from where you're standing. You can measure individual trees, you can estimate distances, you can identify different species. What you cannot easily do is see the entire forest at once. Now imagine climbing into an airplane and looking down. Suddenly the shape becomes obvious. You see clearings, you see rivers, you see hills, you see patterns that were invisible from the ground. Astronomers face a similar challenge with the Milky Way. We are not outside observers, we are residents, and that creates complications. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years across. It contains hundreds of billions of stars, enormous clouds of gas, dark nebulae, star clusters, black holes, magnetic fields, cosmic rays, and countless other structures. The problem is that we occupy a location inside this enormous system. Specifically, the solar system resides about 27,000 light-years from the galactic centre. That's neither particularly close to the centre, nor especially close to the edge. We're simply somewhere within the disk. From this position, trying to understand the galaxy's overall shape becomes a bit like trying to draw a map of an entire city while standing on one street corner. You can gather information, you can measure directions, you can estimate distances, but obtaining the full picture requires patience and creativity. For much of human history, people didn't even know the Milky Way was a galaxy. The pale band stretching across the night sky inspired countless myths and stories. Some cultures saw a celestial river, others imagined a road connecting worlds. Many simply viewed it as a mysterious feature of the heavens. The truth turned out to be far more remarkable. That faint band of light consists of enormous numbers of distant stars, so many in fact that they blend together into a glowing stripe across the sky. The reason the Milky Way appears as a band rather than covering the entire sky is because we live inside its disk. When we look toward the plane of the galaxy, we see countless stars packed together. When we look above or below that plane, the stellar population becomes much thinner. The result is the familiar ribbon of light visible from dark locations. This realization was one of humanity's first clues about our position within a much larger structure. Yet even after astronomers understood that the Milky Way was a galaxy, determining its shape proved difficult. Dust became a major obstacle. Interstellar dust sounds harmless. The word dust often brings to mind a thin layer on a bookshelf, or perhaps something accumulating in neglected corners of a room. Cosmic dust is different. Even relatively small amounts can block visible light extremely effectively. Large regions of the Milky Way remain hidden behind enormous dust clouds. Stars located beyond these clouds may be completely invisible in ordinary observations. It's a little like trying to study a city through dense fog. Buildings exist, roads exist, entire neighborhoods exist, yet visibility remains limited. This is why astronomers rely on different types of light. Infrared observations can penetrate dust more effectively than visible light. Radio waves can reveal structures hidden entirely from optical telescopes. X-rays expose energetic regions. Gamma rays reveal some of the most extreme phenomena in existence. Each wavelength acts like a different set of eyes. No single view tells the whole story. Instead, astronomers combine observations from across the electromagnetic spectrum to create a more complete picture. This process becomes especially important when studying the galactic center. The center of the Milky Way is one of the most fascinating places in the galaxy. It is also one of the hardest places to observe. Between us and the center lie enormous quantities of dust and gas. Visible light telescopes see relatively little. Infrared instruments perform better. Radio telescopes perform better still. Only by combining multiple approaches can researchers examine what is actually happening there. This challenge is particularly relevant to the story of the Fermi Bubbles. After all, the bubbles appear to originate near the galactic center. To understand them, scientists first needed to understand the environment from which they emerged. That turns out to be easier said than done. Imagine trying to investigate the source of smoke while standing inside a crowded city during a heavy fog. Buildings block your view. Streetlights create glare. Traffic generates distractions. The source may be nearby, yet difficult to identify. Studying the center of the Milky Way can feel similar. Astronomers must look through tens of thousands of light-years of intervening material. Every observation contains contributions from multiple sources. Stars overlap, gas clouds overlap, radiation from different objects blends together. Separating one component from another requires careful analysis. This complexity explains why the discovery of the Fermi Bubbles was so surprising. The structures are enormous, yet seeing them clearly required a very specific perspective. Ironically, their size contributed to their invisibility. Small objects often stand out because they appear distinct. Extremely large objects can become difficult to recognize because they blend into the broader background. Consider clouds on Earth. A small cloud immediately catches your attention. A cloud covering the entire sky can become almost invisible because there is nothing obvious to compare it against. The Fermi Bubbles presented a similar challenge. They occupy such a large region that identifying them required careful subtraction of numerous background signals. Only after removing known sources did their shape become apparent. Even then, interpreting what astronomers were seeing required considerable effort. Part of the challenge stemmed from the fact that we're observing the bubbles from the side, or more accurately from inside the structure connected to them. Imagine standing within a giant building and attempting to determine the shape of two massive towers extending from its roof. Your view would be limited. Walls would block certain angles. Distances would be difficult to estimate. You would need measurements from many directions before constructing an accurate model. Astronomers faced a comparable problem. The bubbles extend above and below the galactic plane. We observe them from within that plane. As a result, understanding their true dimensions required extensive modelling. Researchers had to determine how far away various features were. They had to estimate volumes. They had to calculate orientations. Only then could they begin assessing the bubble's actual size and structure. The effort revealed something remarkable. The Fermi bubbles are not minor features attached to the galaxy. They represent major components of the galactic environment. Once identified, they became impossible to ignore. And yet for billions of years they remained entirely unnoticed by any intelligent observer, because the necessary technology did not exist. That fact highlights another interesting aspect of astronomy. The universe does not present itself in convenient ways. Nature offers no obligation to make discoveries easy. Sometimes important structures reveal themselves immediately. Other times they hide behind layers of complexity. The Milky Way is particularly good at creating such challenges. Living inside a galaxy provides extraordinary opportunities. We can study nearby stars in exceptional detail. We can examine local gas clouds. We can investigate planetary systems with remarkable precision. At the same time, our location limits our ability to see the broader structure. It's a trade-off. We gain detail, we lose perspective. Distant observers experience the opposite situation. Consider how astronomers study spiral galaxies elsewhere in the universe. Many appear beautifully organized. Spiral arms stretch outward. Central bulges stand clearly visible. Overall shapes become obvious almost immediately. A single image may reveal more about a galaxy's large-scale appearance than decades of observations conducted from inside one. If intelligent observers lived in another galaxy and pointed powerful telescopes toward the Milky Way, they would likely understand its overall structure more quickly than humanity did. They would see the spiral arms, they would see the central bar, they might even notice the Fermi bubbles relatively easily. Meanwhile, we remain embedded within the system itself, like fish attempting to describe an ocean, or forest dwellers attempting to map an entire continent. The challenge is substantial, yet it also produces some of astronomy's most satisfying achievements. Every improvement in observation technology reveals something new. Radio astronomy transformed our understanding of galactic structure. Infrared astronomy revealed hidden stars. Space telescopes removed atmospheric limitations. Gamma-ray observatories uncovered phenomena impossible to detect from Earth's surface. Each advance expanded our perspective. The discovery of the Fermi bubbles belongs within this broader pattern. The structures were not created by new technology. They already existed. What changed was our ability to perceive them. In many ways, astronomy is less about creating knowledge and more about removing blindness. The universe remains what it is. Our instruments gradually reveal additional layers. A telescope functions much like a key. It unlocks information that was always present. The Fermi telescope provided one such key. Once researchers gained access to detailed gamma-ray maps, the bubbles emerged from the background. The structures had likely been there for millions of years. Humanity simply lacked the tools necessary to recognize them. This realization raises an interesting question. What else might still be hidden within our galaxy? History suggests the answer is probably quite a lot. Every generation of astronomers tends to believe they have achieved a reasonably complete understanding of the cosmos. Then new instruments arrive. Unexpected discoveries follow. Assumptions require revision. The cycle repeats. The Milky Way continues surprising us. The Fermi bubbles serve as an excellent example. They are enormous, energetic, potentially linked to dramatic events in the galaxy's past, yet they remained unknown until the 21st century. If structures of that scale can evade detection for so long, it seems unwise to assume all major galactic mysteries have already been solved. For now, however, The bubbles themselves provide more than enough to investigate. Once astronomers understood where they were located and how difficult they had been to identify, attention shifted toward another fundamental question. Exactly how large were these structures? Numbers in astronomy have a habit of becoming meaningless if we're not careful. Tell someone that a mountain is 1 kilometer tall and they can picture it. Tell someone that a city is 50 kilometers away and they immediately understand the distance. Tell someone that a galaxy contains hundreds of billions of stars spread across 100,000 light years, and the brain politely nods before quietly giving up. The Fermi Bubbles belong firmly in that second category. When astronomers first realized how large these structures were, the challenge wasn't simply measuring them. The challenge was finding ways to communicate their size without causing everyone to stare blankly into space. Because the truth is that the Fermi Bubbles are not merely large, they are staggeringly, almost absurdly large. In fact, one reason the discovery shocked astronomers so much is that the structures occupy a substantial fraction of the Milky Way itself. Let's start with the basic numbers. Each bubble extends approximately 25,000 light-years from the galactic centre. One reaches north of the Milky Way's disk, the other reaches south. Together they span roughly 50,000 light-years from top to bottom. Those figures sound impressive. The problem is that light-year often becomes just another scientific word after a while. We hear it so often that we stop thinking about what it actually means. A light-year is not a measurement of time. It's a measurement of distance. Specifically, it is the distance light travels in 1 year. Light moves at approximately 300,000 kilometers every second. That's fast enough to circle Earth more than 7 times in a single second. Even at that astonishing speed, light requires over 4 years to reach the nearest star beyond our Sun. And it requires 25,000 years to travel from the centre of the Milky Way to the top of one Fermi bubble. Pause for a moment and think about that. 25,000 years ago, humans were still living during the final stages of the last ice age. Mammoths still walked the earth. Agriculture had not yet been invented. Cities did not exist. Written language did not exist. The pyramids were unimaginably far in the future. Yet a beam of light leaving the galactic centre at that moment would only now be reaching the upper edge of one of these structures. That is the scale we're discussing. Sometimes astronomers use comparisons to make such distances easier to grasp. Let's try one. Imagine shrinking the Milky Way until its entire diameter became the length of a football field. In that model, the Fermi Bubbles would still tower above and below the field, like gigantic structures extending far into the air. They would not appear as small decorations attached to the galaxy. They would dominate the scene. This is one reason astronomers became so interested in them. Anything capable of creating structures on that scale must have involved enormous amounts of energy. Small events create small effects. Large effects require large causes. The universe generally follows that rule. What makes the Fermi Bubbles particularly interesting is that they are not isolated objects floating somewhere in intergalactic space. They are directly connected to our galaxy. Imagine discovering that your house has 2 enormous towers extending from its roof. The towers are half the size of the house itself. You somehow never noticed them. Naturally, you would start asking questions. Who built them? Why are they there? When were they constructed? The Milky Way found itself in a similar position. Astronomers suddenly realized that our galaxy possessed structures large enough to compete with many of its most prominent features, and yet they had remained hidden until modern observations revealed them. Interestingly, the bubbles are not only tall, they are also wide. Near their broadest regions, each bubble stretches thousands of light-years across. These are not thin columns. They're enormous volumes of space filled with energetic particles and radiation. If we could somehow travel through one, the journey would take an astonishing amount of time. Suppose, purely for the sake of imagination, that you boarded a spacecraft capable of travelling at the speed of the Voyager probes. Voyager 1 currently moves at roughly 17 kilometers per second. That's extremely fast by human standards. At that speed, crossing a single Fermi bubble would require hundreds of millions of years. Entire species appear and disappear in shorter periods. Continents shift, mountains rise and erode. Meanwhile, your spacecraft would still be making its way through the bubble. Astronomical scales are often difficult because our everyday experience provides no useful reference points. Human life operates on scales of meters, kilometers, years, and decades. Galaxies operate on scales of thousands of light years and millions of years. The gap between those perspectives is enormous. This becomes especially apparent when comparing the bubbles to familiar galactic structures. The Milky Way's central bulge, the dense concentration of stars surrounding the galactic center, spans roughly 10,000 light years. Each Fermi bubble extends significantly farther than that. The Sun itself orbits the galactic center at a distance of approximately 27,000 light years. That means one bubble stretches nearly as far as the distance separating us from the center of the galaxy. In other words, if you could somehow pick up the solar system and place it directly above the galactic center, you would find yourself near the outer edge of the northern bubble. That comparison often surprises people. The solar system feels incredibly far from the galactic center, yet the bubbles reach almost that far vertically. Another useful comparison involves neighboring galaxies. Many dwarf galaxies orbit the Milky Way. Some of these entire galaxies occupy regions comparable to portions of the bubbles. Imagine a structure so large that smaller galaxies could fit comfortably within it. That's the territory we're entering. Of course, size alone doesn't tell the whole story. Volume matters too. Because the bubbles are three-dimensional structures, their total volume becomes enormous. Trying to calculate the exact number is complicated because their shape isn't perfectly spherical. Nevertheless, the amount of space they occupy is staggering. These aren't thin shells. They're vast regions extending tens of thousands of light years into the galactic halo. The galactic halo itself deserves a brief mention. Most people picture galaxies as flat disks. That's understandable. Images of spiral galaxies usually emphasize their disks and spiral arms. But galaxies possess more than just disks. Surrounding the Milky Way is an extended halo containing hot gas, dark matter, globular clusters, and other material. The Fermi bubbles expand into this environment. They rise above and below the crowded stellar disk and push into the more diffuse regions surrounding the galaxy. This makes them particularly valuable for scientists. Because of their enormous size, they interact with large portions of the galactic environment. They influence gas, they influence magnetic fields, they influence the movement of energetic particles. Studying them helps researchers understand processes operating across vast scales. Another fascinating aspect of their size is how symmetrical they appear. Perfect symmetry rarely exists in nature. Most large structures display irregularities. Clouds differ from one another. Mountains vary in shape. Galaxies often exhibit distortions. Yet the Fermi bubbles possess a surprisingly balanced appearance. The northern and southern structures look like mirror images on opposite sides of the galactic plane. This symmetry immediately suggests a central origin. Something near the middle of the Milky Way appears to have influenced both directions simultaneously. The larger the structures became in scientists' calculations, the more compelling that conclusion appeared. After all, creating symmetrical bubbles extending 25,000 light years in opposite directions is not something that happens accidentally. Nature usually requires a powerful and organized mechanism. The scale also provides clues about age. Large structures require time to grow. Even material moving at tremendous speeds cannot instantly fill regions spanning tens of thousands of light years. This realization prompted astronomers to estimate how long the bubbles had been expanding. Their calculations suggested ages measured in millions of years. Compared with the age of the galaxy, that's relatively recent. The Milky Way is more than 13 billion years old. An event occurring a few million years ago is almost yesterday by galactic standards. Imagine condensing the entire history of the Milky Way into a single calendar year. The event responsible for the Fermi Bubbles would occur during the final moments of December 31st. The structures would represent fresh evidence of something that happened surprisingly recently. That finding raised another intriguing possibility. If the bubbles formed recently, perhaps similar events have happened before. Maybe the Milky Way occasionally experiences periods of activity separated by long intervals of relative calm. Perhaps the galaxy has a more dynamic history than its present appearance suggests. Size measurements alone could not answer those questions, but they pointed researchers toward them. The more accurately scientists mapped the bubbles, the more difficult it became to view them as the minor curiosities. These were major galactic structures, historical records written across tens of thousands of light years, evidence that something significant had occurred near the center of our galaxy. There is also a subtle psychological effect associated with discoveries like this. Most people grow up imagining the Milky Way as largely static. Stars move, certainly. Explosions happen occasionally. But the galaxy itself feels permanent and stable. The Fermi Bubbles challenge that intuition. They remind us that galaxies are active systems. They evolve, they change, they release energy, they reshape their environments. Sometimes they produce structures so large that even a civilization capable of building space telescopes can overlook them for years. And perhaps that is one of the most remarkable aspects of the discovery. Not merely that the bubbles are enormous, not merely that they occupy a huge fraction of our galaxy, but that they reveal a Milky Way far more active and eventful than it first appears. Most discoveries in astronomy begin with something visible. A star appears brighter than expected. A planet passes in front of its sun. A galaxy looks distorted. A comet grows a tail. Human beings are naturally comfortable with sight. We trust our eyes. If something can be photographed, we tend to feel that it is real. If it cannot be photographed, things become less intuitive. This creates an interesting problem when discussing the Fermi Bubbles. The structures are enormous. They contain extraordinary amounts of energy. They stretch tens of thousands of light years above and below the Milky Way. And yet, if you somehow travelled far enough away to look back at our galaxy, with ordinary human vision, you wouldn't see them at all. Not even a little. They would be completely invisible. No glowing outlines. No giant balloons floating around the Milky Way. No mysterious shapes hanging in space. Nothing. The bubbles exist, but they do not exist in a form our eyes can detect. That naturally raises a question. If they are invisible, how do astronomers know they are there? And perhaps even more importantly, what exactly are these structures made of? To answer that, we need to talk about a misconception that many people have regarding astronomical photographs. When most people see an image from a telescope, they assume they are looking at something similar to an ordinary photograph. A camera points at an object. Light enters. The image is captured. Simple. Sometimes astronomy works that way. Many beautiful pictures of galaxies, planets, and nebulae are indeed photographs based on visible light. The universe, however, produces far more than visible light. In fact, visible light represents only a tiny fraction of the electromagnetic spectrum. Human eyes evolved to detect a narrow range of wavelengths because those wavelengths happen to be useful on Earth. Nature did not design our eyes to detect every form of radiation in existence. That would have been considerably more complicated. Imagine trying to sleep while simultaneously seeing radio waves, microwave signals, Wi-Fi networks, and every gamma-ray source in the sky. Peaceful evenings might become difficult. Instead, our eyes focus on a relatively small range of wavelengths. Astronomers, on the other hand, are much less limited. They use instruments capable of detecting radiation far beyond human vision. Radio telescopes observe radio waves. Infrared telescopes observe heat signatures. X-ray observatories reveal some of the hottest regions in the cosmos. Gamma-ray telescopes detect the most energetic photons known. Each instrument provides a different view of reality. None of these views is more correct than the others. They're simply different ways of observing the same universe. Think of it like listening to an orchestra. Suppose you could only hear violins. The music would still exist. You would simply miss everything else. Now imagine gradually adding cellos, flutes, drums, and trumpets. The composition becomes richer. The universe works similarly. Visible light is merely one instrument in a much larger orchestra. The Fermi Bubbles reveal themselves primarily through gamma rays. This is one reason they remained hidden for so long. Human eyes cannot detect gamma rays. Ordinary cameras cannot detect gamma rays. Earth's atmosphere blocks most gamma rays before they even reach the ground. As a result, studying them requires specialized spacecraft operating above the atmosphere. The Fermi Gamma Ray Space Telescope was specifically designed for this purpose. Yet even after detecting gamma rays, astronomers still face another challenge. Gamma rays do not produce photographs in the conventional sense. You cannot simply point a camera at a gamma ray source and receive a colourful image. Instead, scientists must detect individual gamma ray photons and reconstruct where they originated. Imagine standing outside during a rainstorm while blindfolded. You cannot see the clouds, you cannot see the rain, but you can feel raindrops landing on different parts of your body. Over time, you begin building a mental map of where the rain is coming from. Gamma ray astronomy works somewhat similarly. The telescope detects incoming photons. Computers record their energies and directions. Thousands, millions, and eventually billions of detections are combined into detailed maps. Those maps reveal structures invisible to ordinary vision. The Fermi bubbles emerge from precisely this process. Astronomers did not photograph them in the traditional sense. They constructed them from data. Every point on a gamma ray map represents measurements accumulated over long periods of observation. The resulting image is less like a snapshot and more like a carefully assembled puzzle. Once scientists recognized the bubbles, attention shifted toward understanding their composition. After all, a structure occupying such a vast region of space must contain something. The simplest answer is energetic particles, lots of them. The bubbles are filled with particles moving at extremely high speeds. Many are traveling close to the speed of light. These particles carry enormous amounts of energy. In astronomy, particles accelerated to such velocities are often called cosmic rays. The name sounds slightly dramatic, but it is entirely accurate. Cosmic rays are energetic particles originating from various astrophysical processes. Supernova explosions create them, neutron stars create them, black holes create them, powerful shock waves create them. The universe is surprisingly good at accelerating particles. In some environments, nature outperforms even our most advanced particle accelerators. The Large Hadron Collider is one of humanity's greatest engineering achievements. Yet cosmic processes routinely accelerate particles to energies that dwarf what we can currently produce. The Fermi bubbles appear to contain vast populations of these energetic particles. Those particles interact with magnetic fields, gas, and radiation. As they do so, gamma rays are produced. The gamma rays become detectable, and that detection allows astronomers to infer what is happening inside the bubbles. The process is a bit like studying wind. You cannot see wind directly. What you observe are its effects. Leaves move, flags flutter, clouds drift. From those observations, you infer the wind's existence. Astronomers use similar reasoning. They observe gamma rays, they observe X-rays, they observe radio emissions. From these clues, they reconstruct the physical conditions inside the bubbles. Interestingly, the bubbles contain more than energetic particles alone. Evidence suggests they also contain extremely hot gas. And when astronomers say hot, they mean something very different from what most people imagine. A summer afternoon might reach 30 degrees Celsius. Boiling water reaches 100 degrees Celsius. The surface of the sun approaches 5,500 degrees Celsius. The gas associated with the Fermi bubbles reaches temperatures measured in millions of degrees. At those temperatures, matter behaves differently. Atoms become ionized. Electrons separate from atomic nuclei. The resulting state is called plasma. plasma is often described as the fourth state of matter. Unlike solids, liquids, and gases, plasma consists of charged particles responding strongly to magnetic fields. The universe contains enormous quantities of plasma. In fact, most visible matter in the cosmos exists in this state. Stars are plasma. Many nebulae are plasma. Large portions of interstellar space contain plasma. The Fermi Bubbles appear to contain significant amounts of it as well. This realization provided another important clue. Whatever created the bubbles was not a gentle event. Generating structures filled with hot plasma across tens of thousands of light years requires tremendous energy. Imagine heating an entire ocean. Now imagine heating something vastly larger than an ocean. Then imagine doing so on galactic scales. The energy requirements become extraordinary. Researchers therefore began investigating additional properties. One particularly fascinating aspect involves magnetic fields. Most people rarely think about magnetic fields beyond refrigerator magnets or compass needles. In reality, magnetic fields permeate the universe. Planets possess them. Stars possess them. Galaxies possess them. The Milky Way itself contains an extensive magnetic network stretching across enormous distances. The Fermi Bubbles appear to interact with these fields in intriguing ways. Radio observations revealed structures extending along portions of the bubbles. These observations suggested organized magnetic activity. Rather than being simple empty cavities, the bubbles seem to contain a complex internal architecture. You might think of them as giant cosmic weather systems. Not weather in the familiar terrestrial sense, of course. There are no rainstorms or snowfalls occurring inside them, but they contain moving particles, magnetic structures, energy flows, and evolving conditions. They are dynamic environments. Another question naturally emerged. How dense are the bubbles? The answer is surprisingly counterintuitive. Despite their immense size, they are extraordinarily diffuse. Space is mostly empty. Even regions containing gas often contain very little by everyday standards. The best vacuum chamber ever constructed on Earth would still contain more particles than many regions of interstellar space. The Fermi Bubbles are no exception. Their material is spread across such enormous volumes that densities remain extremely low. Yet because the structures themselves are so vast, the total amount of energy involved remains enormous. This combination often appears throughout astronomy. Tiny densities, gigantic volumes, extraordinary totals. Human intuition struggles because our daily experiences provide no equivalent examples. We don't routinely deal with objects tens of thousands of light years across. As researchers continued examining the bubbles, another mystery appeared. The edges looked surprisingly sharp. This observation may sound minor, but it carried major implications. Imagine releasing smoke into a room. Initially, the boundaries are obvious. Over time, the smoke disperses, the edges blur, the distribution becomes increasingly uniform. Many large astronomical structures behave similarly. Sharp boundaries tend to soften with age. Yet the Fermi Bubbles maintained relatively distinct edges. That suggested either a younger age or ongoing processes helping preserve their structure. Once again, the observations hinted at something energetic, something powerful, something capable of shaping matter and energy across enormous distances. Scientists also discovered evidence of shock fronts associated with portions of the bubbles. Shock fronts occur when material moves faster than surrounding conditions can accommodate smoothly. A familiar example is a sonic boom produced by a supersonic aircraft. The aircraft compresses air ahead of it. A shockwave forms, energy propagates outward. Similar phenomena occur throughout the universe. Supernova explosions generate shockwaves. Stellar winds generate shockwaves. Galactic outflows generate shockwaves. The presence of shocks around portions of the bubble suggested expansion and energetic activity. The structures were not passive objects simply sitting in space. They were interacting with their environment. Every new observation reinforced the same conclusion. The bubbles represented evidence of a major event in the Milky Way's past. By this stage, astronomers had accumulated an impressive collection of clues. They knew the bubbles emitted gamma rays. They knew they contained energetic particles. They knew they contained extremely hot plasma. They knew magnetic fields played an important role. They knew the structures were enormous. They knew significant amounts of energy were involved. Yet one fundamental question remained unanswered. What actually created them? Knowing what fills a structure does not automatically reveal its origin. Suppose you discover a gigantic crater. You can measure it. You can analyze its contents. You can study surrounding rocks. But determining whether it formed from a volcanic eruption or an asteroid impact requires additional investigation. The Fermi Bubbles presented a similar challenge. Astronomers understood many of their properties. The source remained uncertain. Two major possibilities gradually emerged. One pointed toward the supermassive black hole lurking at the centre of the Milky Way. The other pointed toward vast numbers of massive stars and supernova explosions. Both explanations possess strengths. Both explanations face challenges, and determining which one best matched the evidence would become one of the most fascinating investigations in modern astronomy. Black holes occupy a curious place in popular culture. They're often portrayed as cosmic vacuum cleaners, endlessly sucking everything around them into darkness. It's an understandable image. The name itself encourages that interpretation. Black hole, a hole in space, something that swallows things. Simple. The reality is both more complicated and far more interesting. A black hole is not really a hole. It is a region where gravity has become extraordinarily strong. Strong enough that beyond a certain boundary, called the event horizon, escape becomes impossible. Not because something is physically pulling you inward like a giant cosmic drain. Rather, because space and time themselves have become so distorted that every possible path leads deeper inside. Even light cannot escape, hence the darkness. But despite their reputation, black holes spend much of their time doing very little. If our sun suddenly became a black hole, while somehow retaining the same mass, Earth's orbit would remain essentially unchanged. We would continue circling it exactly as before. We would certainly have other problems. A missing sun tends to create difficulties, but the orbit itself would remain stable. Gravity depends on mass, not on whether that mass happens to be a star or a black hole. This brings us to the object sitting at the centre of the Milky Way. Astronomers call it Sagittarius A star. The name is pronounced roughly as Sagittarius A star, and despite sounding like a piece of advanced software or perhaps an unusually ambitious household appliance, it is actually the supermassive black hole at the heart of our galaxy. The word supermassive deserves emphasis. This is not an ordinary black hole. Most black holes form when massive stars die. Their masses typically range from a few times the mass of the Sun to perhaps dozens of times larger. Sagittarius. A star belongs to a completely different category. It contains roughly 4 million times the mass of our Sun. 4 million. That number is difficult to visualize. Imagine placing 4 million suns together in one location. Not side by side, not spread across a region of space. Concentrated, compressed into a relatively compact volume. The result would still struggle to compete with the density found inside Sagittarius A star. Yet despite containing so much mass, the black hole itself remains surprisingly difficult to observe directly. After all, black holes do not emit light. That's part of their defining characteristic. Astronomers therefore detect them indirectly. They observe their influence on nearby objects, much like a detective reconstructing the presence of an invisible suspect from footprints and fingerprints. In the case of Sagittarius A star, the evidence became impossible to ignore during the late 20th century. Researchers began tracking stars orbiting the galactic centre. These stars moved astonishingly fast. Some completed their orbits in only a few decades. Others accelerated dramatically as they approached an apparently empty point in space. The motions were unmistakable. Something extremely massive occupied the center, something compact, something invisible. By carefully measuring stellar orbits over many years, astronomers calculated the mass of the hidden object. The answer left little room for alternative explanations. Only a supermassive black hole fit the observations. The discovery was so important that later work on these measurements contributed to a Nobel Prize. Today, Sagittarius A star is accepted as the central black hole of the Milky Way, and in many ways, it appears surprisingly quiet. This may sound odd. After all, a 4 million solar mass black hole hardly seems like the type of object one would describe as quiet. Yet compared to similar black holes elsewhere in the universe, Sagittarius A star behaves with remarkable restraint. Many galaxies contain active galactic nuclei. These are regions where supermassive black holes consume large quantities of matter. As gas falls inward, it heats dramatically. Radiation pours into space. Jets form. Entire galaxies can become flooded with energy originating from their centers. Some active galaxies shine so brightly that the central region outshines every star in the galaxy combined. Against that backdrop, Sagittarius A star looks almost sleepy. Today, it consumes relatively little material. Its energy output remains modest. Astronomers certainly observe activity. The black hole occasionally produces flares. Gas swirls around it. Magnetic fields twist and reconnect. Interesting things happen. But compared with truly active galactic nuclei, our central black hole appears calm, at least now. That final phrase became increasingly important after the discovery of the Fermi Bubbles, because calm today does not necessarily mean calm yesterday. Imagine visiting a volcano. The slopes are quiet, birds nest nearby. Birds. Grass grows undisturbed. Nothing appears dangerous. Yet geological evidence reveals enormous eruptions in the past. The volcano may be peaceful now, but its history tells a different story. Astronomers began wondering whether Sagittarius A star might fit a similar pattern. Perhaps the black hole currently resides in a relatively quiet phase. Perhaps millions of years ago conditions were very different. The idea gained traction because astronomers already knew that supermassive black holes can produce structures resembling the Fermi Bubbles. Across the universe, telescopes have observed gigantic outflows emerging from galactic centers. Some extend for hundreds of thousands of light years. Others stretch even farther. Jets launched near black holes can carry enormous amounts of energy across vast distances. Entire regions of intergalactic space can be influenced by these processes. If distant galaxies could create such structures, why not the Milky Way? The possibility immediately attracted attention. The Fermi Bubbles appeared symmetrical. One extended north, one extended south. Both seemed connected to the galactic center. That geometry looks suspiciously consistent with activity originating from Sagittarius A star. The more scientists studied the bubbles, the harder it became to ignore that connection. Of course, correlation is not proof. Astronomers needed evidence. Fortunately, the galaxy had left behind clues. One clue involved timing. Researchers estimated that the bubbles formed several million years ago. Interestingly, other observations suggested unusual activity near the galactic center during roughly the same period. Ancient events leave traces, not always obvious traces, not always complete traces, but traces nonetheless. As astronomers pieced together these records, a picture began emerging. It seemed increasingly possible that Sagittarius A star experienced a significant outburst in the relatively recent past. The question then became obvious. What exactly happened? Black holes do not simply decide to become active. They require fuel. Specifically, they require matter. Gas clouds, stars, dust, anything capable of falling inward. When sufficient material approaches a black hole, it does not plunge directly into the event horizon. Instead, it usually forms an accretion disk. Imagine water circling a drain. The material spirals inward. Friction increases, temperatures rise, enormous quantities of energy are released. The process can become extraordinarily efficient. In fact, accreting black holes convert matter into energy more efficiently than nuclear fusion. A star like the Sun generates energy through fusion. A feeding black hole can exceed that efficiency significantly. This is one reason active galactic nuclei rank among the brightest objects in the universe. Even relatively small amounts of infalling matter can produce extraordinary energy outputs. Suppose a large cloud of gas drifted towards Sagittarius, a star, several million years ago. Or perhaps a cluster of stars migrated inward. Maybe a molecular cloud wandered too close. Any of these scenarios could potentially provide fuel. As material accumulated, the black hole's activity level might have increased dramatically. The resulting energy release could have launched powerful outflows above and below the galactic plane. Over time, those outflows might inflate structures resembling the Fermi Bubbles. The basic concept sounds straightforward. Reality, naturally, is more complicated. One challenge involves understanding exactly how black holes launch material outward. At first glance, this seems contradictory. Black holes pull things in. Why would they produce outflows? The answer involves magnetic fields and angular momentum. Matter falling toward a black hole often carries substantial rotational motion. It cannot simply drop straight inward. Instead, it forms a rapidly spinning disk. Magnetic fields threading through the disk become twisted and amplified. Under certain conditions, these fields can channel energy away from the black hole. Jets form, material accelerates. Enormous amounts of energy escape into surrounding space. Remarkably, some of the most powerful outflows in the universe originate from objects famous for trapping everything nearby. Nature occasionally enjoys irony. Observations of other galaxies provide dramatic examples. Astronomers have photographed jets extending hundreds of thousands of light years. These structures influence star formation. They heat surrounding gas. They alter entire galactic environments. Compared to those colossal systems, the Fermi Bubbles seem almost modest. Almost. Yet for the Milky Way, they represent a major event. Another intriguing piece of evidence emerged from studies of X-ray emissions near the galactic center. Researchers identified features that appeared consistent with past energetic activity. Additional observations revealed structures known as Rosetta bubbles, which may be related to the Fermi Bubbles themselves. These observations strengthen the case that something substantial happened near Sagittarius, a star. The central black hole increasingly resembled a suspect with both motive and opportunity. Still, scientists remained cautious. Astronomy rarely rewards premature conclusions. Alternative explanations continue to compete for attention. Massive star formation events could potentially generate large-scale outflows. Clusters of supernova explosions could inject enormous energy into surrounding gas. Perhaps the bubbles represented the cumulative effect of stellar activity rather than a black hole eruption. The debate remained active, and that is precisely what made the investigation so interesting. Unlike many discoveries where evidence quickly points toward a single explanation, the Fermi Bubbles presented multiple plausible scenarios. Each possessed strengths, each possessed weaknesses. Researchers therefore continued gathering data, comparing models, testing predictions, looking for distinguishing signatures. Meanwhile, Sagittarius, a star, remained exactly where it had always been: invisible, massive, quiet, a 4 million solar mass object sitting at the center of the galaxy. If it truly created the bubbles, then millions of years ago it behaved very differently from the object we observe today. And that possibility carries an intriguing implication. The Milky Way we see now may not be representative of the Milky Way's recent past. Our galaxy feels stable because human lifetimes are short. Even recorded history spans only a tiny fraction of galactic time. Events separated by millions of years appear disconnected to us. For a galaxy, however, They may be part of an ordinary cycle. Periods of calm, periods of activity, periods of transformation. The Fermi Bubbles hint that the Milky Way may occasionally become far more energetic than it appears today. If that is true, then our galaxy possesses a hidden history of dramatic events occurring deep within its core. And to uncover that history, astronomers needed to look beyond the present-day appearance of Sagittarius A star and ask a broader question. What if the Milky Way itself was once a much more violent place than anyone had imagined? If you could somehow travel backwards several million years and visit the Milky Way, you might not immediately notice anything unusual. The spiral arms would still be there, the stars would still fill the sky, the galaxy would still look familiar from a distance. Yet beneath that familiar appearance, something very different may have been happening deep within its core. Today, the Milky Way feels relatively peaceful. Astronomers certainly observe supernova explosions. Stars are born and die. Black holes consume material. Cosmic rays race through space. Interesting things happen everywhere. But compared with some galaxies observed across the universe, ours appears surprisingly calm. The centre of the Milky Way is not blazing with enormous jets. It is not flooding intergalactic space with radiation. It is not behaving like one of the extreme active galaxies that dominate astronomical photographs. For many years, that calm appearance shaped how scientists thought about our galaxy. The Milky Way was viewed as mature, stable, reasonably well behaved, not boring certainly, but not particularly violent either. Then the Fermi Bubbles entered the picture. Suddenly, astronomers found themselves facing evidence that suggested a very different history. Because the bubbles themselves represent something important. They are not merely structures, they are scars, and scars imply events. Nobody gets a scar without a story behind it. The same principle applies on galactic scales. When researchers began calculating how much energy would be required to create the Fermi Bubbles, the numbers quickly became difficult to ignore. Whatever happened near the galactic centre was not a minor occurrence. This was not the astronomical equivalent of a small campfire. This was closer to a geological eruption visible across an entire continent. The exact amount of energy remains an active area of research, but many estimates place it in a range equivalent to millions of supernova explosions. That figure alone forces a reconsideration of how we view our galaxy. For perspective, consider a single supernova. When a massive star reaches the end of its life, the resulting explosion can briefly outshine an entire galaxy. The energy released is staggering. A supernova produces more energy in a few moments than the sun will generate during its entire lifetime. Now imagine millions of such events contributing an equivalent amount of energy, not necessarily occurring simultaneously, not necessarily in the same way, but contributing to an overall energy budget of similar magnitude. That is the scale researchers found themselves dealing with. The Milky Way suddenly seemed much less quiet. Astronomers began asking an important question. If such an event happened recently enough to create the Fermi Bubbles, what other evidence might still remain? Fortunately, the universe tends to preserve clues, not forever. Eventually, even enormous structures fade, but millions of years is often short enough for traces to survive. Researchers started examining the galactic centre with renewed interest. What they found was intriguing. The central regions of the Milky Way contain evidence of past activity that appears significantly more energetic than what we observe today. Some of the evidence comes from enormous clouds of gas. Other clues emerge from X-ray observations. Additional hints appear in the distribution of cosmic rays and magnetic fields. Individually, these observations might not seem dramatic. Taken together, however, they suggest a central region that has experienced periods of intense activity. One particularly fascinating clue involves something known as the Magellanic Stream. This vast structure of gas stretches across enormous distances and interacts with the Milky Way's environment. Some researchers have proposed that energetic events originating from the galactic centre may have influenced surrounding material in ways that remain detectable today. The details are complex. The broader implication is simpler. The centre of the Milky Way appears to have been more active in the past, far more active. This realization aligns with something astronomers already knew from studying other galaxies. Galaxies change, not gradually in every respect, sometimes dramatically. A galaxy that appears calm today may have experienced explosive activity millions of years ago. A galaxy that appears active today may eventually settle into a quieter phase. The universe rarely remains static. Everything evolves, everything changes, everything follows cycles extending far beyond human timescales. This can be difficult to appreciate because our perspective is so limited. Human civilization spans only a few thousand years. Recorded history occupies an even shorter interval. Compared with galactic evolution, those timescales barely register. Imagine watching a tree for 5 seconds and attempting to understand its entire life cycle. You would see almost nothing, no growth, no seasonal changes, no aging. The tree would appear essentially frozen. That is roughly how galaxies appear to us. Our observation period is extraordinarily short compared with the processes we are trying to study. The Fermi Bubbles provide a rare opportunity to glimpse recent galactic history. They act almost like a recording. Not a perfect recording, not a complete one, but a record nonetheless, evidence preserved across tens of thousands of light years, evidence suggesting that something major happened within the last few million years. Interestingly, the idea of a more violent Milky Way initially felt surprising, because people tend to associate dramatic galactic activity with distant exotic systems. When astronomers publish images of active galaxies, the photographs often look extraordinary. Jets stretch across space. Bright central regions dominate the image. Immense structures become visible. Those galaxies feel different from ours, almost alien. Yet the Fermi Bubbles hint that the Milky Way may not be fundamentally different at all. Perhaps we are simply observing it during a quieter period. Think about volcanoes again. A dormant volcano can appear peaceful for centuries. Forests grow on its slopes. Animals make homes nearby. Visitors walk around comfortably. The landscape seems stable. Then geological evidence reveals ancient eruptions that reshaped entire regions. The volcano has not changed identity, only its current state. Galaxies may behave similarly. Periods of activity come and go. The underlying system remains the same. One reason this idea gained support involves comparisons with other spiral galaxies. Astronomers have observed numerous galaxies containing large-scale outflows, extending above and below their disks. Some of these outflows appear connected to black holes. Others appear connected to intense episodes of star formation. In either case, energetic events occurring near the galactic center influence enormous surrounding regions. The Fermi Bubbles fit comfortably within that broader pattern. Instead of making the Milky Way unusual, they may actually make it more typical. That possibility is somewhat amusing. The discovery initially seemed extraordinary because the bubbles were unexpected. Yet they may ultimately reveal that our galaxy behaves much like many others. It simply happened to be hiding the evidence. Researchers also began investigating whether ancient activity from the galactic center might have affected Earth's environment. This is a complicated question. The answer appears to be no in any dramatic sense. The events responsible for the bubbles occurred far away. The solar system remained safely distant from the galactic center. Nevertheless, the possibility highlights how interconnected galactic processes can be. Events occurring tens of thousands of light years away can leave signatures detectable across enormous regions of space. Galaxies are not collections of isolated parts. They are interconnected systems. Changes in one region can influence conditions elsewhere. Another interesting aspect involves timing. Estimates suggest the bubbles formed only a few million years ago. That sounds like a very long time. In human terms, it certainly is. In galactic terms, it is surprisingly recent. The Sun requires roughly 230 million years to complete one orbit around the galactic centre. Compared with that orbital period, a few million years barely qualifies as recent history. Imagine reading a biography covering 80 years of someone's life. An event occurring 6 months ago would feel recent. The Fermi Bubbles occupy a similar position in the Milky Way's timeline. They are relatively fresh, recent enough that their structure remains visible, recent enough that traces of the responsible event continue to persist, recent enough to provide astronomers with valuable clues. As scientists examined those clues, a picture gradually emerged. The Milky Way likely experienced an energetic episode originating near its centre. The event injected enormous energy into surrounding regions. Material expanded outward. Particles accelerated. Hot gas filled vast volumes of space. Millions of years later, the resulting structures remain visible as the Fermi Bubbles. The broad outline seemed increasingly plausible. Yet a crucial question remained unresolved. What exactly triggered the event? This is where the investigation became particularly interesting. Two major suspects continued competing for attention. One involved the supermassive black hole Sagittarius A star. The other involved intense bursts of star formation and supernova activity. Both explanations could potentially account for the observed energy. Both possessed supporting evidence. Both remained scientifically respectable possibilities. The challenge lay in determining which scenario better matched the available data. Astronomers therefore began focusing more closely on the black hole itself. Could Sagittarius A star have experienced a feeding frenzy several million years ago? Could infalling gas have transformed the currently quiet object into a much more active source of energy? Could a black hole eruption inflate structures spanning tens of thousands of light years? By the time astronomers had measured the size of the Fermi Bubbles, estimated their age, and analysed the energetic particles inside them, one conclusion was becoming difficult to avoid. Something powerful happened near the centre of the Milky Way. Not merely powerful by human standards, not merely powerful by planetary standards, powerful on a galactic scale. The bubbles were simply too large, too energetic, too organised, too symmetrical. Nature can certainly produce chaos. Many astronomical structures are irregular. Clouds of gas twist into strange shapes. Supernova remnants expand unevenly. Star-forming regions often appear messy and unpredictable. The Fermi Bubbles looked different. They seemed deliberate. Not deliberate in the sense that anyone created them intentionally, of course. Rather, they appeared to be the consequence of a focused physical process originating near the galactic centre. One structure above, one structure below, both stretching outward from the same region. It was almost as though something at the heart of the Milky Way had taken a deep breath millions of years ago and blasted energy into space. Naturally, astronomers began looking for suspects, and very quickly, attention returned to Sagittarius A star, the supermassive black hole lurking at the centre of our galaxy. At first glance, the idea seems reasonable. After all, black holes are famous for extreme behaviour. They distort space and time, they consume matter, they produce enormous amounts of energy under the right conditions. If a giant mysterious structure appears near the centre of a galaxy, blaming the central black hole feels almost inevitable. But science is not about assigning blame. It is about following evidence, and evidence had to answer an important question. Could Sagittarius A star actually produce something like the Fermi Bubbles? The answer appears to be yes, at least in principle. To understand why, we need to revisit a common misunderstanding about black holes. People often imagine black holes as objects that only pull things inward. The reality is more complicated. Under certain conditions, black holes become some of the most effective engines in the universe. Oddly enough, the energy doesn't come from matter disappearing. It comes from matter struggling not to disappear. Imagine gas drifting toward a black hole. The gas possesses momentum. It cannot simply fall straight inward. Instead, it begins orbiting. Those orbits become tighter and tighter. The gas forms a rotating accretion disk. As material circles closer to the event horizon, friction increases dramatically. Temperatures soar, magnetic fields strengthen, particles accelerate. The result is an environment so energetic that it can outshine entire galaxies. The black hole itself remains dark. The surrounding activity becomes spectacular. Some active black holes generate jets. These jets consist of particles accelerated to extraordinary velocities. In certain cases, the particles approach the speed of light. The jets emerge from regions near the black hole and travel enormous distances into space. Astronomers have observed examples stretching hundreds of thousands of light years. Some extend even farther. The scale is difficult to exaggerate. These are among the largest structures produced by individual objects in the universe. Once scientists considered this phenomenon, the Fermi Bubbles suddenly looked much less mysterious. Not explained, but less mysterious. Because the bubbles resembled the aftermath of exactly the kind of event that active black holes are known to produce. There was one complication. Sagittarius A star does not currently behave like an active black hole. Today it appears relatively quiet. If you compared it with the supermassive black holes powering quasars and active galaxies, it would seem almost lazy. Astronomers observe occasional flares. Gas occasionally falls inward. Interesting things happen, but nothing on the scale required to inflate structures 25,000 light-years tall. This forced researchers to consider an important possibility. What if Sagittarius A star was different in the past? The universe does not require objects to remain in a single state forever. Stars evolve, galaxies evolve, black holes evolve, conditions change, fuel supplies change, energy outputs change. Perhaps the Milky Way's central black hole experienced a period of intense activity several million years ago before settling into its current quiet state. The idea was not only plausible, it was expected. Astronomers had already observed similar behavior elsewhere. Many galaxies appear active for limited periods. Eventually, the available fuel decreases, activity fades, the galaxy becomes quieter. Millions of years later, another influx of gas may reignite the process. These cycles can continue repeatedly throughout galactic history. From that perspective, Sagittarius A star might simply be resting between active phases. One clue supporting this possibility came from observations of other galaxies. Across the universe, astronomers have documented enormous lobes, bubbles, and outflows associated with central black holes. Some bear remarkable similarities to the structures observed in the Milky Way. The details vary, every galaxy is different, yet the overall pattern remains familiar. A central source injects energy. Material expands outward. Large-scale structures form. When scientists compared these systems with the Fermi Bubbles, the resemblance became difficult to ignore. Another clue involved the bubbles themselves. Remember those relatively sharp edges discussed earlier? Sharp boundaries often suggest a rapid energetic event. Imagine throwing a stone into a pond. The resulting waves spread outward. Clear boundaries appear. Energy propagates through the surrounding environment. The Fermi Bubbles display characteristics consistent with large-scale expansion. Something seems to have pushed outward. Something energetic. Something originating near the galactic center. A black hole outburst naturally fits that description. Researchers began building computer simulations to test the idea. This is where astronomy often becomes surprisingly creative. Scientists cannot travel millions of years into the past. They cannot observe the original event directly. Instead, they construct mathematical models. Various scenarios are tested, parameters are adjusted, predictions are compared against observations. Suppose Sagittarius A star experienced a major accretion event. How would energy propagate through surrounding gas? How large would resulting structures become? How quickly would they expand? What shape would emerge? The simulations produced encouraging results. Many black hole-driven models generated structures broadly resembling the observed bubbles. Not perfectly. Nature rarely provides perfect matches, but close enough to demonstrate plausibility. The black hole hypothesis remained very much alive. Then another fascinating piece of evidence emerged. Astronomers studying gas clouds far from the galactic centre discovered signs of illumination that appeared difficult to explain. Certain clouds seemed to carry evidence of past X-ray activity, almost like cosmic photographs exposed by an ancient flash. The interpretation remains an active area of research, but some scientists suggest these observations may represent echoes of a more active Sagittarius A star. Imagine lightning illuminating distant mountains. Long after the flash itself disappears, evidence remains. Astronomers may be observing something similar. Ancient activity recorded indirectly in surrounding material. If correct, the implication is remarkable. It would mean the central black hole was significantly more energetic in the recent past. Exactly what the bubble hypothesis requires. Still, questions remained. How much energy would be necessary? The numbers are substantial. Inflating structures spanning tens of thousands of light years is not trivial. Researchers estimate that Sagittarius A star would have needed to consume a considerable amount of matter. Fortunately, galaxies contain plenty of potential fuel. The central regions of the Milky Way are rich in gas. Massive molecular clouds drift through the area. Stars occasionally wander too close. Material accumulates. Over millions of years, opportunities for feeding events arise naturally. The black hole does not need to consume an entire galaxy. A relatively modest amount of infalling matter can release extraordinary energy. This is one of the most surprising aspects of black hole physics. The efficiency is astonishing. Converting even a small amount of mass into energetic outflows can have galaxy-wide consequences. In practical terms, the bubbles might represent the aftermath of a brief but dramatic feeding episode, a cosmic meal with unusually large consequences. Of course, scientists are cautious about accepting a hypothesis simply because it sounds impressive. Alternative explanations continued competing for attention. Many researchers pointed out that intense star formation could potentially generate similar structures. After all, clusters of massive stars produce strong stellar winds. Supernova explosions inject enormous amounts of energy into surrounding gas. Given enough stars, the cumulative effect could become substantial. The question became one of comparison. Which explanation better matched the observations? Black hole activity, massive stellar activity, or perhaps some combination of both? Interestingly, the black hole model gained support from the symmetry of the bubbles. The structures appear centered almost perfectly on Sagittarius A star. That alignment is difficult to dismiss as coincidence. If the bubbles originated elsewhere, one might expect noticeable offsets. Instead, the geometry points directly toward the galactic center. It is almost as though the bubbles are drawing an arrow toward the black hole. Not proof, but certainly suggestive. Researchers also examined the age estimates. Many calculations suggest the bubbles formed several million years ago. That time frame aligns reasonably well with potential episodes of enhanced activity near Sagittarius A star. Again, the evidence was not conclusive, but it was consistent, and in science, consistency matters. The more independent observations support the same explanation, the stronger that explanation becomes. One particularly intriguing aspect of the black hole hypothesis involves scale. Supermassive black holes possess a remarkable ability to influence regions vastly larger than themselves. Sagittarius A star is relatively compact compared with the structures surrounding it, yet its gravitational influence extends across enormous distances. If active, its energetic influence could extend even farther. This creates a fascinating contrast. The object itself occupies a comparatively small region. The consequences of its activity span tens of thousands of light years. It's a bit like discovering that a tiny valve controls water flow throughout an entire city. The controlling mechanism appears small. The effects are enormous. That realization has changed how astronomers think about galaxies. For many years, galaxies were viewed primarily as collections of stars. Today, researchers increasingly recognize the importance of central black holes. These objects may regulate star formation, influence gas dynamics, shape galactic evolution. The Fermi Bubbles fit naturally into that broader picture. If Sagittarius A star created them, then our own galaxy provides another example of a central black hole influencing its environment on a massive scale. The evidence was substantial, the geometry was suggestive, the timing worked. By this point in the investigation, the case against Sagittarius A star looked surprisingly strong. The Fermi bubbles appeared centered on the galactic core. The energy requirements seemed compatible with a black hole outburst. Computer simulations produced structures that looked remarkably similar to the observations. Astronomers had plenty of reasons to take the idea seriously. But science has a habit of becoming most interesting precisely when things seem straightforward. Because there was another explanation, a very different explanation. One that did not require a supermassive black hole suddenly becoming active. One that relied instead on something much more familiar. Stars. A lot of stars. An almost ridiculous number of stars. And more specifically, an almost ridiculous number of stars exploding. At first glance, this might sound less impressive than a black hole. Black holes tend to dominate public attention. They bend space. They trap light. They create dramatic headlines. Stars, by comparison, can seem almost ordinary. The problem with that perspective is that stars are only ordinary when viewed one at a time. When massive stars begin forming in huge numbers, entire galaxies can change. To understand why, let's imagine a region where star formation suddenly accelerates. Astronomers call such an event a starburst. A starburst occurs when gas clouds collapse rapidly and begin producing stars at rates far above normal. Instead of creating a few stars here and there, the galaxy suddenly enters a period of intense stellar construction. The result resembles a cosmic building boom. New stars appear everywhere. Massive stars form in large numbers. The environment becomes crowded, energetic, and increasingly chaotic. Now here's where things become important. Massive stars do not live very long. This often surprises people. The bigger stars are not the longest lived. In fact, the opposite is true. Large stars burn through their fuel at astonishing rates. They live fast and die young. A star many times more massive than the Sun may survive only a few million years before reaching the end of its life. And when that end arrives, it tends to be spectacular. The star explodes as a supernova. We've already discussed how energetic supernovae are. A single one briefly rivals the brightness of entire galaxies. It releases enormous quantities of energy. Shock waves expand through surrounding space. Heavy elements scatter outward. The explosion can influence regions dozens or even hundreds of light years across. One supernova is impressive. 10 supernovae are extraordinary. 1,000 supernovae become difficult to imagine. Now imagine millions, not necessarily all occurring at once, not even within the same century, but occurring across a relatively concentrated region over astronomical timescales. Suddenly, the energy budget begins approaching the levels needed to explain the Fermi bubbles. This realization led many astronomers to consider a different possibility. Perhaps the bubbles were not created by a black hole eruption. Perhaps they were inflated by enormous numbers of massive stars forming and dying near the galactic center. The idea was not as exotic as it might sound. The central regions of galaxies often contain active star-forming environments. The Milky Way is no exception. Near the galactic center, conditions can become quite extreme. Gas densities are high. Molecular clouds contain vast quantities of material. Stars form continuously. Some regions produce large populations of massive stars. Those stars generate strong stellar winds. Even before exploding, they influence their surroundings. A stellar wind is exactly what it sounds like. Matter flows outward from a star into surrounding space. For a star like the Sun, the solar wind is relatively gentle. For very massive stars, the situation becomes considerably more dramatic. These stars can eject enormous amounts of material. The winds travel at tremendous speeds. Over time, they carve cavities into surrounding gas. They generate shock waves. They inject energy into the interstellar medium. Now imagine thousands of massive stars doing this simultaneously. Their winds begin interacting. Shock waves collide. Gas gets heated. Energy accumulates. The surrounding environment becomes increasingly turbulent. Then the explosions start. One supernova follows another, then another, then another. The cumulative effect can become extraordinary. Astronomers refer to the resulting phenomenon as a galactic wind. The name sounds almost peaceful. The reality is anything but. Galactic winds are large-scale outflows of gas and energetic particles driven by stellar activity. They can transport material thousands of light-years from its origin. They can reshape entire regions of a galaxy. They can carry heavy elements into surrounding space. In some galaxies, galactic winds become so powerful that they influence future generations of star formation. This is important because the Fermi Bubbles look remarkably similar to structures produced by galactic winds in other galaxies. When astronomers observe starburst galaxies elsewhere in the universe, they often find enormous lobes of hot gas extending above and below galactic disks. These outflows can reach impressive sizes. Sometimes they resemble giant plumes. Sometimes they resemble bubbles. Sometimes they resemble vast fountains of energetic material rising from galactic centers. The similarities caught researchers' attention immediately. Perhaps the Milky Way experienced a major starburst episode a few million years ago. Perhaps massive stars formed in huge numbers. Perhaps their combined winds and supernova explosions generated enough energy to inflate the bubbles. The concept was entirely plausible, and unlike some exotic theories, it relied on processes already known to occur throughout the universe. This gave the stellar explanation considerable credibility. Evidence supporting the idea also existed. Astronomers had identified regions near the galactic center where substantial star formation had occurred in the past. Clusters of massive stars still remain. Ancient stellar populations provide clues about previous activity. The galactic center has clearly experienced periods when star formation rates exceeded what we observe today. The question was whether those episodes were energetic enough. Researchers began running simulations. If larger numbers of stars formed near the center, how would their combined winds behave? How much gas would they push outward? What shapes would emerge? Would the resulting structures resemble the Fermi Bubbles? In many cases, the answer appeared encouraging. The models produced large-scale outflows extending above and below the galactic plane. Hot gas filled expanding regions. Shock fronts developed. Some simulated structures resembled observation surprisingly well. This was not what astronomers hoping for a simple answer wanted to see. The black hole explanation already looked plausible. Now the stellar explanation looked plausible too. Instead of narrowing the mystery, the evidence seemed to broaden it. One particularly interesting aspect of the starburst hypothesis involves timing. Massive stars evolve quickly. A starburst event occurring several million years ago naturally produces supernova activity on similar timescales. The age estimates derived from the Fermi Bubbles appeared broadly compatible with that scenario. Again, not proof, but compatibility matters. The more observations a model can explain simultaneously, the more attractive it becomes. Another advantage of the stellar explanation is that it distributes energy production across many sources. This can help explain certain features of large-scale galactic outflows. Instead of requiring one dramatic eruption, the bubbles could represent the cumulative effect of countless events occurring over extended periods. Think about the difference between a single volcanic eruption and centuries of smaller eruptions gradually reshaping a landscape. Both can produce impressive results. The mechanisms differ. The outcome may appear similar. The Fermi bubbles might reflect a comparable situation, not one enormous event. Rather, a prolonged period of stellar activity gradually injecting energy into the surrounding environment. Researchers also examined chemical signatures. Supernova explosions manufacture heavy elements. When those elements spread through space, they leave detectable traces. By studying the composition of gas associated with the bubbles, astronomers hoped to determine whether stellar activity played a major role. The results proved intriguing but not definitive. Some observations appeared consistent with stellar contributions. Others seemed easier to explain through black hole-driven activity. The mystery persisted. Interestingly, this situation is not unusual in astronomy. Nature often refuses to choose between competing explanations. Reality sometimes combines multiple processes simultaneously. Researchers therefore began considering a third possibility. Perhaps both explanations were partially correct. Perhaps Sagittarius A star contributed. Perhaps star formation contributed as well. After all, the galactic center is a busy place. Massive stars and a supermassive black hole coexist within the same environment. Their activities influence one another. Gas-feeding star formation may also feed the black hole. Energy released by one process may affect the other. The resulting system becomes complex, very complex. One reason the combined scenario gained attention is that galaxies rarely operate through single mechanisms. Many processes occur simultaneously. Stars form, stars explode, black holes accrete matter, gas flows inward and outward, magnetic fields evolve, cosmic rays propagate through space. Trying to isolate one influence completely can become difficult. The Milky Way's center may represent precisely that kind of environment. Yet even if both processes contributed, scientists still wanted to know which one dominated. Which engine supplied most of the energy? The answer matters because it affects how we understand galactic evolution. If black holes drive structures like the Fermi bubbles, then central black holes play a particularly important role in shaping galaxies. If stellar activity dominates instead, then star formation becomes the primary architect. Determining the balance between those influences helps astronomers understand not only our galaxy, but countless others. The debate therefore extended far beyond the Milky Way. The Fermi bubbles became a laboratory for studying fundamental galactic processes. Researchers compared observations from radio telescopes. They analysed X-ray maps. They examined gamma-ray distributions. Every dataset added another piece to the puzzle. And yet, despite years of work, the case remained surprisingly competitive. The black hole explanation possessed strengths. The stellar explanation possessed strengths. Neither side achieved a decisive victory. In some ways, that uncertainty reflects the complexity of the universe itself. We often prefer simple stories, one cause, one effect, one answer. Reality frequently behaves differently. Large structures may emerge from multiple interacting processes. The Milky Way's history may involve both stellar explosions and black hole activity contributing to the same phenomenon. If that turns out to be true, the Fermi bubbles become even more interesting. Not because they reveal one dramatic event, but because they reveal an entire ecosystem of galactic activity operating over millions of years. For now, however, one thing remained clear. Whatever created the bubbles released enormous amounts of energy. That energy did not simply disappear after the structures formed. It continued interacting with surrounding material. It continued influencing magnetic fields. It continued propagating through the galactic halo. And evidence suggested that the bubbles themselves may still be evolving even today, which raises another fascinating question. What if these giant structures are not merely ancient relics from the Milky Way's past? What if they are still growing, still expanding, and still carrying the echoes of whatever created them millions of years ago? When people hear about the Fermi bubbles for the first time, they often imagine them as ancient relics. The word relic feels appropriate. After all, these structures may have formed millions of years ago. They are enormous. They preserve evidence from a distant chapter of the Milky Way's history, and they appear to be connected to events that happened long before humans existed. It is tempting to picture them as frozen monuments hanging motionless above and below the galaxy, like giant cosmic fossils, like footprints preserved in stone, like ancient ruins drifting through space. The reality appears far more interesting. The universe rarely stands still. Galaxies do not stand still. Gas does not stand still. Magnetic fields do not stand still. And the Fermi Bubbles almost certainly do not stand still either. In fact, one of the most fascinating discoveries made after the bubbles were identified is that these structures appear to be dynamic. They are not simply leftover shapes sitting quietly in space. They interact with their surroundings, they evolve, they expand, and in a very real sense they may still be carrying energy outward through the Milky Way even today. To understand why astronomers think this, we need to discuss what happens after a large energetic event occurs. Imagine dropping a stone into a pond. The moment the stone strikes the water, energy begins moving outward. Ripples spread across the surface. The original splash may last only a second, but the consequences continue travelling long afterward. Now imagine scaling that idea up from a pond to a galaxy. If something released enormous amounts of energy near the centre of the Milky Way several million years ago, the effects would not disappear immediately. They would continue propagating outward. Gas would move, shock waves would travel, particles would accelerate, magnetic fields would respond. The aftermath could remain active for millions of years. This is precisely what makes the Fermi Bubbles so valuable. They are not merely evidence that something happened. They are evidence that is still evolving. Researchers began suspecting this fairly early in the investigation. One clue came from the bubbles' sharp boundaries. Remember how unusual those boundaries appeared? Astronomical structures often become fuzzy over time, material disperses, energy spreads out, distinct edges gradually soften. Yet the Fermi Bubbles possess surprisingly well-defined outlines. That observation immediately raised questions. Why do the edges remain so clear? What process is maintaining them? One possibility is that the bubbles are younger than we initially assume. Another possibility is that they continue interacting with surrounding material in ways that preserve their structure. Either explanation suggests ongoing activity, neither suggests a completely dormant system. The idea became even more compelling when astronomers examined evidence for shock fronts. Shock fronts are common throughout the universe. Whenever material moves rapidly through surrounding gas, shock waves can form. A familiar example occurs when a supersonic aircraft exceeds the speed of sound. Air cannot move out of the way quickly enough. A shock wave develops. The resulting sonic boom carries energy outward. Something similar happens in space. The difference is that the scales become vastly larger. Supernova explosions generate shock fronts. Stellar winds generate shock fronts. Galactic outflows generate shock fronts. And evidence suggests the Fermi Bubbles contain them as well. This is important because shock fronts often indicate motion, they indicate expansion. They indicate energy continuing to interact with the surrounding environment. If the bubbles were completely inactive, such features would be more difficult to explain. The existence of shock structures hints that the story is not entirely finished. The consequences of the original event may still be unfolding. Astronomers obtained additional clues from X-ray observations. Several studies identified enormous structures extending beyond the gamma-ray boundaries of the bubbles themselves. These features appeared to contain extremely hot gas. Temperatures reached millions of degrees. Such conditions are difficult to maintain without substantial energy. Researchers began wondering whether they were observing the outer consequences of bubble expansion. Perhaps the bubbles had driven material outward. Perhaps that material continued interacting with the galactic halo. Perhaps the entire system remained active on scales larger than initially recognized. The possibility gained attention because galaxies are not empty. This is an important point that often gets overlooked. Space is extraordinarily sparse compared with Earth, yet galaxies still contain significant amounts of material. Gas fills large regions, hot plasma drifts through the halo, magnetic fields stretch across enormous distances. Dark matter contributes gravitational influence. When the Fermi bubbles expand, they do not move through perfect emptiness. They encounter an environment, and whenever moving material encounters an environment, interactions occur. Think about a ship travelling through water. The ship moves forward, waves form, currents change, the surrounding ocean responds. Now replace the ship with a structure tens of thousands of light years tall. Replace the ocean with the galactic halo. The principle remains surprisingly similar. Movement creates consequences. Astronomers therefore began asking a natural question. How fast are the bubbles expanding? Unfortunately, answering that question is not easy. The structures are enormous. The timescales are immense. Human lifetimes are short. We cannot simply observe them for a few years and watch obvious changes occur. The universe is not always that cooperative. Instead, researchers estimate expansion speeds indirectly. They analyze temperatures. They examine shock waves. They study particle energies. They construct models describing how the bubbles likely evolved. The resulting estimates vary depending on assumptions. Some suggest expansion speeds measured in hundreds of kilometers per second. Others indicate even faster motion. Regardless of the exact value, the implication remains similar. The bubbles appear to have expanded rapidly following their formation, and portions of that expansion may still be continuing today. This brings us to an intriguing realization. The Milky Way is not merely a collection of stars orbiting peacefully around the galactic center. It is a dynamic system. Energy moves, gas moves, particles move, structures grow and evolve. The Fermi bubbles provide a dramatic example. Sometimes astronomy can feel distant. Black holes seem remote. Galaxies seem abstract. Events occurring millions of years ago seem disconnected from daily life. The bubbles challenge that feeling. They remind us that our galaxy possesses an active history. Not ancient history alone, ongoing history. Processes initiated millions of years ago continue influencing conditions today. In some sense, the bubbles are still carrying the memory of their creation outward through space. Researchers also discovered evidence that cosmic rays continue interacting within the bubbles. This is significant because cosmic rays lose energy over time. Their behavior provides clues about age, transport processes, and ongoing activity. Some observations suggest that energetic particles continue moving through the structures. The bubbles are not simply empty shells. They remain filled with energetic material. That material continues producing observable emissions. Gamma rays continue arriving at our detectors. Radio waves continue revealing hidden features. The structures remain active participants in the galactic environment. Another fascinating aspect involves scale. Human beings naturally struggle with long time scales. A century feels long. A millennium feels enormous. Millions of years feel almost unimaginable. Yet galaxies routinely operate on such timescales. The Fermi bubbles illustrate this beautifully. Suppose the original event occurred 6 million years ago. To us, that sounds ancient. To the Milky Way, it is relatively recent. The galaxy is more than 13 billion years old. 6 million years represents only a tiny fraction of its history. The bubbles, therefore, resemble fresh scars more than ancient fossils. They may look old from a human perspective. From a galactic perspective, they remain remarkably young. This distinction helps explain why ongoing expansion remains plausible. The structures simply have not existed long enough for all traces of their formation to disappear. Large systems evolve slowly. A feature spanning 50,000 light-years does not suddenly become static. Its energy disperses gradually. Its influence persists. Its interactions continue. The bubbles, therefore, offer astronomers a rare opportunity. Instead of studying an event that is completely finished, researchers can examine consequences still unfolding. That makes the structures enormously valuable. Every observation provides information about both the past and the present. The bubbles reveal what happened. They also reveal what is still happening. Interestingly, some studies suggest that the Fermi bubbles may have experienced multiple episodes of activity, rather than a single event. The evidence remains debated, but the possibility is intriguing. Perhaps the bubbles were not inflated all at once. Perhaps several energetic episodes contributed. Maybe the galactic center released energy repeatedly over time. If true, the structures become even more dynamic. Instead of representing one eruption, they might record an extended history of galactic activity. Imagine discovering that a volcano erupted not once but repeatedly over thousands of years. The resulting landscape would preserve evidence of multiple events layered together. The Fermi bubbles may contain similar complexity. Researchers continue investigating this possibility. As observations improve, new details emerge, and every new detail reinforces a broader lesson. The Milky Way is not frozen. It is alive with processes operating across immense scales. The bubbles themselves illustrate this perfectly. They expand, they interact, they transport energy, they influence surrounding material, they continue evolving long after the original event ended. Perhaps the most remarkable aspect is that all of this is happening within our own galaxy. For generations, humanity looked toward distant galaxies and assumed the most dramatic activity occurred elsewhere. The Fermi bubbles tell a different story. Our galaxy possesses its own large-scale outflows, its own energetic history, its own evidence of dramatic events. And those events are not merely historical curiosities, their consequences continue shaping the Milky Way today. If there is one feature of the Fermi bubbles that has consistently puzzled astronomers since their discovery, it is not their size, it is not their age, it is not even the question of what created them. The real puzzle is something much simpler: their edges. At first glance, that may not sound particularly mysterious. After all, everything has edges. Mountains have edges, clouds have edges, continents have edges. Why should anyone care about the boundaries of two enormous structures floating above and below the Milky Way? The answer becomes obvious the moment you remember how large the Fermi bubbles actually are. These are structures extending roughly 25,000 light-years in opposite directions from the galactic center. They are filled with energetic particles. They contain hot gas. They interact with magnetic fields. They have likely existed for millions of years, and yet their outlines remain surprisingly sharp. That should not happen easily. Imagine lighting a small campfire. Smoke rises into the air. Initially, you can clearly see the boundary between the smoke and the surrounding atmosphere. Give it enough time, however, and those boundaries disappear. The smoke spreads. The edges become fuzzy. Everything gradually blends together. The same principle applies throughout nature. Whenever energy, particles, or gas spread through an environment, mixing tends to occur. Sharp boundaries soften. Distinct structures become blurred. Astronomers expected something similar with the Fermi bubbles. Instead, observations revealed something quite different. The edges remained surprisingly well defined, almost unnaturally so. The discovery immediately raised questions. Why had the bubbles not simply diffused into the surrounding galactic halo? Why had energetic particles not escaped more uniformly? Why did the structures still appear organized after millions of years? The more scientists investigated, the stranger the problem became, because maintaining those boundaries requires something invisible, something capable of organizing matter and energy across tens of thousands of light years, something acting like an internal framework, a hidden skeleton, and eventually researchers realized they may have found it: magnetic fields. Now, magnetic fields rarely receive the same public attention as black holes. This is somewhat unfortunate because magnetic fields are among the most important structures in the universe. In many ways, they're also among the least intuitive. You can see a star, you can photograph a galaxy, you can observe a planet. Magnetic fields are different. They are invisible. You never see the field itself, you only see its effects. A compass needle turning, iron filings arranging themselves into patterns, charged particles changing direction. The field remains hidden. The consequences reveal its presence. The universe contains magnetic fields almost everywhere. Earth has one. Without it, life on our planet would face serious difficulties. The magnetic field helps shield Earth from energetic particles arriving from space. It protects our atmosphere. It influences auroras. It quietly performs its job every day. The Sun possesses magnetic fields too. In fact, many of the Sun's most dramatic behaviors originate from magnetic activity. Solar flares, coronal mass ejections. Sunspots all involve magnetic fields storing and releasing enormous amounts of energy. Stars have magnetic fields. Planets have magnetic fields. Nebulae have magnetic fields. Entire galaxies have magnetic fields. The Milky Way is threaded with a vast magnetic network stretching across enormous distances. Most of the time, these fields remain invisible, yet they influence the motion of charged particles throughout the galaxy, and that influence may explain the remarkable structure of the Fermi Bubbles. The story began becoming clearer when astronomers started observing the bubbles at wavelengths beyond gamma rays. Gamma rays revealed the structures. Other observations began revealing what was happening inside them. Radio telescopes proved especially useful. Radio astronomy often functions like a cosmic detective. It reveals things that ordinary telescopes cannot. Energetic particles moving through magnetic fields produce radio emissions. By studying those emissions, astronomers can infer the existence and arrangement of magnetic structures. When researchers examined the regions associated with the Fermi bubbles, they found something fascinating. The radio observations suggested organized magnetic fields extending through large portions of the bubbles. Not random fields, not chaotic fields, organized fields, fields with structure, fields capable of guiding energetic particles. This discovery changed how scientists thought about the bubbles. Previously, many researchers imagined them primarily as enormous volumes of hot gas and energetic particles. Now another ingredient appeared increasingly important: magnetism. And once magnetism entered the picture, several mysteries suddenly became easier to explain. Consider energetic particles. Without guidance, particles tend to spread out. Given enough time, they diffuse throughout their surroundings. Boundaries become less distinct. Structures blur. Yet charged particles do not move randomly when magnetic fields are present. Instead, they tend to follow magnetic field lines. The fields act almost like invisible highways. Particles travel along preferred routes. Movement becomes organized. The resulting structures can remain coherent for much longer periods. This immediately suggested a possible explanation for the sharp edges. Perhaps magnetic fields were acting like containment walls. Not solid walls, of course. Nothing so simple. Rather, the fields could be restricting particle motion, keeping energetic particles concentrated inside the bubbles, preserving their shape, maintaining their boundaries. The idea gained support as more observations accumulated. Researchers identified enormous radio structures extending above and below the galactic center. Some appeared connected to the bubbles themselves. Others resembled giant filaments threading through the surrounding environment. Collectively, these observations painted a picture of a galaxy filled with magnetic architecture, an architecture that may have been shaped by the same event responsible for the bubbles. Imagine inflating a balloon. The balloon expands. Material moves outward. Now imagine that expansion occurring inside a magnetic environment. The expansion stretches field lines, twists them, reorganizes them. The resulting structure becomes a combination of gas, particles, and magnetic fields evolving together. Something very similar may have happened within the Fermi bubbles. The event that created them may also have reshaped the magnetic environment surrounding the galactic center. One particularly intriguing discovery involved gigantic radio lobes extending through regions associated with the bubbles. These structures contained evidence of cosmic ray electrons spiraling through magnetic fields. Whenever charged particles spiral around magnetic field lines, they emit a type of radiation known as synchrotron radiation. The name sounds technical. The underlying idea is surprisingly simple. Charged particles changing direction release energy. The emitted radiation becomes observable, and by studying that radiation, astronomers can learn about both the particles and the fields guiding them. The observations revealed something remarkable. The magnetic fields associated with the bubbles appeared surprisingly strong, not extraordinarily strong compared with certain extreme environments, but strong enough to matter, strong enough to influence particle transport, strong enough to affect the long-term evolution of the structures. This helped explain why the bubbles remained visible after millions of years. The magnetic framework appeared to be preserving order. Without that framework, the bubbles might have dispersed far more quickly. The particles responsible for the observed emissions would spread out. The boundaries would become diffuse. The overall structure might fade into the galactic halo. Instead, the bubbles remained recognizable. Another clue came from the symmetry of the system. The northern and southern bubbles display broadly similar characteristics. That symmetry extends beyond the gamma-ray observations. Magnetic structures appear organized in ways that reflect the overall geometry. This suggests a common origin. Something happened near the galactic center. Energy flowed outward. Magnetic fields responded. The resulting architecture developed on both sides of the galaxy. The symmetry itself became evidence. Nature can certainly produce asymmetrical outcomes, yet the bubbles repeatedly display patterns suggesting coordinated large-scale processes. The magnetic fields appear to be part of that story. Interestingly, the fields may also help explain how energetic particles travel such enormous distances. This is another challenge astronomers faced. The bubbles contain particles carrying significant energy. Those particles should gradually lose energy over time, yet observations indicate substantial populations still exist throughout large portions of the structures. How did they get there? How were they transported? Magnetic fields provide a possible answer. Rather than wandering randomly, particles could travel along organized pathways. The fields effectively guide their motion. This allows energetic particles to reach distant regions while maintaining the observed structure. The concept resembles transportation networks on Earth. Roads do not create vehicles, railways do not create trains, yet transportation becomes dramatically more efficient when organized routes exist. Magnetic fields may perform a similar role within the bubbles. They provide structure, they provide guidance, they influence movement, and they help maintain coherence across astonishing distances. As researchers continued examining these possibilities, another fascinating idea emerged. Perhaps the magnetic fields are not merely passive participants. Perhaps they actively shape the bubbles themselves. This distinction matters. A passive field simply responds to events. An active field influences those events. The difference is subtle but important. Magnetic fields store energy. They can release energy. They can redirect flows of material. They can influence shock waves. In some environments, magnetic processes dominate behavior. The sun provides a familiar example. Many solar eruptions are fundamentally magnetic phenomena. Without magnetism, the sun would behave very differently. Could something similar be happening inside the bubbles? Perhaps. The answer remains an active area of research. Scientists continue investigating exactly how important magnetic fields are. New observations regularly refine existing models. Computer simulations become increasingly sophisticated. Every year brings additional insights, yet one conclusion appears increasingly secure. The Fermi bubbles are not simply giant clouds of energetic particles. They are magnetized structures, complex structures, dynamic structures, structures supported by an invisible framework extending across tens of thousands of light years, and that realization transforms how we view them. Instead of picturing two giant empty cavities floating above and below the Milky Way, astronomers increasingly see them as enormous magnetic ecosystems, regions where particles, plasma, shock waves, and magnetic fields interact continuously. Regions still evolving millions of years after their formation. Regions revealing hidden aspects of how galaxies function. Perhaps the most remarkable aspect of all this is scale. Human beings discovered electromagnetism only recently compared with the length of our species' history. Yet magnetic fields have been shaping galaxies for billions of years, long before Earth formed, long before life appeared, long before anyone wondered what existed beyond the night sky. The hidden magnetic skeleton of the Fermi Bubbles represents one more reminder that much of the universe operates through processes we cannot directly see. The structures that dominate reality are not always visible. Sometimes the most important frameworks remain hidden until careful observations reveal their effects. If our galaxy contains structures like these, are they unique, or are similar bubbles hiding around other galaxies throughout the universe? One of the easiest mistakes to make in astronomy is assuming that something unusual must also be unique. The universe has a way of humbling that assumption. Again and again, astronomers discover an object that seems extraordinary, a strange planet, an unusual star, a mysterious structure. At first, it appears completely unique. Then better instruments arrive, more observations accumulate, and suddenly similar examples begin appearing elsewhere. What once looked like a cosmic exception turns out to be part of a much larger pattern. The Fermi Bubbles present exactly this kind of question. When astronomers first identified them in 2010, the structures seemed astonishing. Two giant lobes extending tens of thousands of light years above and below the Milky Way, filled with energetic particles, visible in gamma rays, potentially linked to ancient activity in the galactic center. The discovery immediately raised an obvious question. Are these bubbles something special about our galaxy? Or are we simply seeing a process that happens throughout the universe? In other words, if intelligent observers lived in another galaxy and pointed their telescopes toward the Milky Way, would they shrug and say, "Yes, another galaxy with giant bubbles"? Or would they stare in surprise? Answering that question required astronomers to look outward, far outward, beyond the Milky Way, beyond our local neighborhood, toward the countless other galaxies scattered throughout the cosmos. Fortunately, the universe provides plenty of examples. Current estimates suggest there are hundreds of billions, perhaps even trillions, of galaxies in the observable universe. They come in many varieties. Some are small, some are enormous, some form stars rapidly, others are relatively quiet, some possess active black holes, others appear dormant. Each galaxy represents a natural experiment conducted over billions of years, and hidden within those experiments are clues about whether structures like the Fermi Bubbles are common or rare. At first, the answer seemed uncertain. Part of the difficulty came from perspective. Ironically, astronomers often have an easier time studying the large-scale structure of distant galaxies than they do studying their own. As we've discussed before, living inside the Milky Way creates observational challenges. A distant observer sees the entire galaxy at once, we do not. Because of this, astronomers began examining other galaxies for evidence of large-scale outflows extending above and below their disks. The results were fascinating. Structures resembling the Fermi Bubbles started appearing almost everywhere researchers looked. Not identical structures, not perfect copies. Nature rarely repeats itself with that level of precision, but unmistakably similar phenomena. One of the most famous examples comes from a galaxy known as Messier 82. Astronomers often refer to it as the cigar galaxy because of its elongated appearance. Located roughly 12 million light-years away, it has become one of the best studied examples of a starburst galaxy. And it is anything but quiet. The central regions of Messier 82 are undergoing intense star formation. Massive stars are being created at extraordinary rates. Supernova explosions occur frequently. The environment is chaotic, energetic, violent. The consequences are visible even in photographs. Enormous streams of hot gas rise above and below the galactic disk. These outflows extend thousands of light years into surrounding space. When astronomers compare them with the Fermi Bubbles, the similarities are difficult to ignore. Both involve energy moving outward from galactic centers. Both create large-scale structures. Both influence surrounding environments. The difference is that Messier 82 is currently active. The Milky Way appears relatively calm. This comparison immediately suggests an intriguing possibility. Perhaps the Fermi Bubbles represent evidence that our galaxy once looked more like Messier 82 than it does today. Perhaps we are seeing the aftermath of a starburst phase that has already ended. Another interesting example comes from galaxies containing active galactic nuclei. These are galaxies where central supermassive black holes are actively consuming matter. As material spirals inward, enormous amounts of energy are released. The resulting activity can launch gigantic jets and inflate vast lobes of energetic material. Astronomers have observed examples spanning hundreds of thousands of light years. Some extend well beyond the visible boundaries of their host galaxies. Compared with these monsters, the Fermi Bubbles appear almost modest. Almost. The important point is that the underlying physics looks familiar. A central energy source injects material and energy into surrounding space. Large structures form. Gas becomes heated. Particles accelerate. Magnetic fields respond. The resulting system evolves over millions of years. Whether the source is a black hole or a starburst, the broad pattern remains recognizable. This realization changed how researchers thought about the Milky Way. Instead of viewing the bubbles as an isolated curiosity, astronomers began placing them within a much larger family of galactic phenomena. The Milky Way suddenly looked less unusual. In some ways, that made the discovery even more exciting. Science often becomes most powerful when individual observations connect to broader patterns. Finding one strange object is interesting. Discovering that the object belongs to a larger category is transformative. The Fermi Bubbles started looking less like a cosmic accident and more like part of a fundamental galactic process. Researchers also examined radio galaxies. These systems provide some of the most dramatic examples of large-scale outflows in the universe. Powerful jets emerge from central black holes and travel enormous distances through intergalactic space. At the ends of these jets, giant lobes form. The lobes can become truly enormous. Some exceed the size of the galaxies that created them. These structures differ from the Fermi Bubbles in important ways. The details of their formation are not identical, yet they demonstrate something important. Galaxies possess the ability to reshape their environments on extraordinary scales. The Milky Way is no exception. Another fascinating comparison involves our nearest large galactic neighbour, the Andromeda Galaxy. Located approximately 2.5 million light-years away, Andromeda provides astronomers with an invaluable opportunity. It is close enough to study in detail, yet distant enough to view as an entire system. Observations have revealed evidence of energetic activity associated with Andromeda's central regions. Researchers have identified large-scale structures extending outward from the galaxy. Some may represent ancient outflows, others remain under investigation. The details continue to evolve as observations improve. What matters for our story is that Andromeda appears to have experienced energetic events as well. This is significant because Andromeda and the Milky Way share many characteristics. Both are large spiral galaxies. Both contain supermassive black holes. Both possess complex histories of star formation. If Andromeda displays evidence of giant outflows, the idea that the Milky Way does too becomes even more plausible. In a sense, the two galaxies begin resembling relatives with similar family histories, different individuals, similar experiences. The more astronomers looked, the more examples they found. Some galaxies showed evidence of black hole-driven bubbles. Others showed evidence of starburst-driven bubbles. Some displayed structures visible in radio wavelengths. Others revealed themselves through X-rays or gamma rays. The details varied enormously, yet the fundamental concept kept reappearing. Galaxies generate outflows. Galaxies release energy. Galaxies create bubbles. Galaxies leave behind enormous structures recording episodes of past activity. This broader perspective helps answer an important question. Are the Fermi bubbles unusual? Yes and no. Their specific size, shape, and history are unique to the Milky Way. No two galaxies are exactly alike. Every system follows its own evolutionary path. In that sense, the bubbles are special. But the underlying phenomenon appears surprisingly common. Galaxies throughout the universe seem capable of producing similar structures. The Milky Way may simply be revealing its own version of a process occurring across cosmic history. This conclusion carries an interesting implication. For many years, humanity viewed the Milky Way as a relatively ordinary spiral galaxy. Then the Fermi bubbles were discovered, making our galaxy seem more dramatic. Now, after comparing the Milky Way with countless others, astronomers are arriving at a slightly different picture. The bubbles may actually reinforce the idea that the Milky Way is fairly typical, not because the structures themselves are ordinary, they are not, but because galaxies often appear to experience episodes of energetic activity. The Milky Way seems to be participating in a broader cosmic pattern. There is something comforting about that. The galaxy we call home is not standing apart from the rest of the universe. It is behaving like a galaxy, sometimes calm, sometimes active, sometimes creating structures so large they remain visible for millions of years. As observations improved, another realization emerged. These giant bubbles are not merely consequences of galactic activity. They may actively influence how galaxies evolve. Energy injected into surrounding gas can affect future star formation. Outflows can remove material from central regions. Magnetic fields can transport particles across enormous distances. In some cases, bubbles may help regulate galactic growth itself. This idea has become increasingly important in modern astronomy. Galaxies are not passive collections of stars. They are self-regulating systems. Processes occurring near their centres can influence conditions across vast regions. The Fermi bubbles may represent one example of that regulation in action. Researchers continue investigating exactly how significant their impact might be. Could they influence future star formation? Could they alter the galactic halo? Could they help redistribute energy throughout the Milky Way? These questions remain active areas of study. What is already clear, however, is that the bubbles connect our galaxy to a much larger story. A story involving galaxies throughout the observable universe. A story involving black holes, starbursts, magnetic fields, and enormous outflows. A story demonstrating that galaxies are dynamic systems capable of reshaping themselves over time. And perhaps most intriguingly, a story suggesting that the Milky Way's recent past may hold important clues about its future. Because if galaxies throughout the universe repeatedly experience energetic episodes that create giant bubbles, an obvious question follows: what does that mean for our own galaxy? What does the existence of the Fermi bubbles tell us about the future evolution of the Milky Way? And could similar events happen again someday in the distant future? One of the most natural questions people ask after learning about the Fermi bubbles is whether they should be worried. It's an understandable reaction. Astronomers discover two enormous structures stretching 25,000 light-years above and below the Milky Way. The structures appear to be connected to an energetic event near the centre of our galaxy. The event may have involved a supermassive black hole, or perhaps millions of exploding stars. Either way, the energy involved was extraordinary. Naturally, people wonder what happens next. Could it happen again? Would Earth be affected? Does the existence of the bubbles mean the Milky Way is becoming more active or less active? And perhaps most interestingly, what do these structures tell us about the future of our galaxy? These questions are exactly the kind astronomers love. Not because the answers are simple, in fact many of them are not. Rather, because they force us to think about galaxies as living systems, not living in the biological sense, of course. Galaxies do not breathe, they do not think, they do not possess intentions. Yet they evolve, they change, they experience periods of activity and periods of calm, they recycle material, they transform themselves over billions of years. The Fermi Bubbles provide a rare glimpse into that process. For much of human history, the Milky Way appeared permanent, stable, unchanging. The stars looked the same generation after generation. The pale band of light crossing the night sky seemed eternal. Even after astronomy revealed that galaxies evolve, it remained difficult to feel that evolution on a personal level. Most galactic processes occur over immense timescales. The changes are too slow for human observers to notice directly. The Fermi Bubbles are different. They represent evidence of a significant event that happened surprisingly recently in galactic terms, not billions of years ago, not even hundreds of millions of years ago, a few million years ago. That distinction matters. Imagine reading the biography of an 80-year-old person. An event that occurred 70 years ago feels distant. An event that occurred last year feels recent. The Milky Way is over 13 billion years old. An energetic event occurring several million years ago is comparatively fresh. The bubbles remind us that our galaxy is still evolving, not in the distant past, right now. One thing the bubbles clearly demonstrate is that the centre of the Milky Way is capable of becoming much more active than it appears today. This may be the most important lesson they offer. For decades, Sagittarius A star looked relatively quiet. Astronomers knew it existed. They knew it contained millions of solar masses. They knew it occasionally produced flares. But compared with active galactic nuclei elsewhere in the universe, it seemed almost sleepy. The Fermi Bubbles challenge that perception. They suggest that the current state of Sagittarius A star may not represent its normal state across cosmic history. Instead, the black hole may cycle through different levels of activity, periods of calm, periods of feeding, periods of energetic outflow, periods of relative dormancy. If that interpretation is correct, then the future of the Milky Way may involve additional active episodes, not necessarily tomorrow, not next year, not even next million years, but eventually. Galactic timescales are patient. One of the easiest mistakes humans make when thinking about astronomy is assuming that current conditions are permanent. History repeatedly demonstrates otherwise. Stars evolve, planets evolve, galaxies evolve, black holes evolve. The fact that Sagittarius A star appears quiet today does not guarantee that it will remain quiet forever. All it takes is fuel, a large cloud of gas drifting inward, a molecular cloud destabilizing, a concentration of material finding its way toward the central black hole. Once fuel becomes available, activity can increase dramatically. This possibility is not speculative. Astronomers observe such behavior throughout the universe. Many galaxies display evidence of repeated active phases. Some appear calm today but reveal signs of ancient outbursts. Others currently shine brightly but may eventually settle into quieter states. The Milky Way likely participates in the same cycle. The bubbles may be evidence of one previous episode, perhaps not the first, almost certainly not the last. This realization transforms how we think about our galaxy. Instead of viewing the Milky Way as a static collection of stars, astronomers increasingly view it as a dynamic system with a long and eventful history. The bubbles are part of that history. They also provide clues about how galaxies regulate themselves. This is an area of research that has become increasingly important over the past few decades. For a long time, astronomers struggled with a question: why don't galaxies form stars as quickly as simple models predict? After all, many galaxies contain enormous amounts of gas. Gas forms stars. More gas should mean more stars. Yet observations revealed that star formation often proceeds much more slowly than expected. Something seemed to be regulating the process. Something was preventing galaxies from converting all available gas into stars at maximum speed. The answer appears to involve feedback. Feedback is one of the most important concepts in modern astrophysics. A process occurs. The process generates consequences. Those consequences influence the original process. The cycle continues. For example, star formation creates massive stars. Massive stars produce winds and supernovas. Those winds and explosions can heat surrounding gas. Hot gas becomes harder to collapse into new stars. The result is a self-regulating system. The more star formation occurs, the more resistance develops. Black holes may perform a similar function. When a central black hole becomes active, it injects energy into its surroundings. That energy can heat gas. It can drive material outward. It can influence future star formation. The Fermi Bubbles may represent a visible example of this feedback in action. If so, they are more than historical curiosities. They are part of the mechanism through which galaxies control their own evolution. Imagine a thermostat in a house. The thermostat does not generate heat directly. Instead, it helps regulate conditions. The bubbles may reflect a similar regulatory process operating on galactic scales. Energy released near the center influences the broader environment. The environment responds. Future evolution changes accordingly. The Milky Way becomes a self-adjusting system rather than a passive collection of stars. This perspective has profound implications. It means the future of the galaxy depends not only on the stars we see today, but also on processes occurring deep within its core. Another lesson concerns the galactic halo. For many years, astronomers focused primarily on the visible disk of the Milky Way. That makes sense. The disk contains most of the stars people associate with the galaxy. The spiral arms are there, the sun is there, most familiar structures are there. The halo received less attention. Yet the Fermi Bubbles demonstrate that the halo is not merely empty space surrounding the galaxy. It is an active environment. Hot gas fills it. Magnetic fields thread through it. Energetic particles move through it. Large-scale structures interact with it. Future studies of the Milky Way will almost certainly pay greater attention to these regions. The bubbles have effectively expanded our understanding of where the galaxy begins and ends. They reveal that important processes occur far beyond the visible disk. The future of the Milky Way cannot be understood by studying stars alone. It requires understanding the entire galactic ecosystem. The bubbles also offer clues about the role of magnetic fields in galactic evolution. Before their discovery, many discussions of galaxy evolution focused primarily on gravity and gas dynamics. Those remain crucial factors. Yet the bubbles highlight the importance of magnetism. Magnetic fields appear to help organize energetic particles. They influence outflows. They preserve large-scale structures. They may regulate how energy moves through galactic environments. Future models of galactic evolution increasingly incorporate these effects. The hidden magnetic skeleton revealed by the bubbles is not merely a curiosity. It is a fundamental component of the system. Then there is the question many listeners quietly wonder about. What does all of this mean for Earth? Fortunately, the answer is reassuring. Very little, at least directly. The event responsible for the bubbles occurred near the galactic center. The solar system sits approximately 27,000 light-years away. That distance provides substantial protection. Even if Sagittarius A star experienced another energetic episode in the future, Earth would remain far from the source. The Milky Way is enormous. Distances that seem modest on a galactic map are unimaginably vast in practical terms. We are not living next door to the black hole. We are living in an entirely different neighbourhood. This is one reason astronomers can study these events with fascination rather than concern. The bubbles reveal important aspects of galactic evolution without presenting any immediate danger. The larger significance lies in what they teach us. And what they teach us is that galaxies are far more dynamic than they initially appear. The night sky encourages an illusion of permanence. Stars seem fixed. Constellations seem timeless. The Milky Way appears serene. Beneath that appearance, however, enormous processes continue unfolding. Gas moves. Stars form. Stars die. Black holes feed. Magnetic fields evolve. Energy flows through structures tens of thousands of light years across. The Fermi Bubbles are evidence of this hidden activity. They remind us that galaxies possess histories, not abstract histories, physical histories recorded in matter and energy, histories that can be reconstructed millions of years later. Perhaps the most exciting implication concerns future discoveries. The bubbles themselves remained hidden until the 21st century, not because they were small, not because they were distant, because we lack the tools to recognize them. That fact should inspire a certain humility. If structures spanning 50,000 light years can remain undiscovered for so long, what else might still be waiting? Future observatories will provide better gamma-ray maps, better radio observations, better X-ray surveys. New instruments will reveal new structures. The Milky Way may contain additional surprises hidden within its halo. The bubbles may be only the beginning. Every generation of astronomy expands the visible universe, not by changing reality. Reality remains what it always was. Instead, we expand our ability to perceive it. The Fermi Bubbles represent one step in that process, a reminder that discovery does not end simply because we happen to live inside the system being studied. In some ways, the most interesting lessons offered by the bubbles concern perspective. For centuries, humanity looked at the Milky Way and saw a beautiful band of stars. Now we know that hidden behind that familiar appearance are giant structures larger than many galaxies, invisible structures, energetic structures, structures carrying evidence of events millions of years old. And those structures suggest that the Milky Way's future will continue to involve change, activity, and evolution. Not dramatic change on human timescales. The galaxy is far too large for that. But change nonetheless. The same processes that created the bubbles have not vanished from the universe. Black holes still feed, stars still explode, galactic winds still blow, energy still moves through space. Eventually, perhaps millions of years from now, the Milky Way may produce new outflows, new bubbles, new structures. Future civilizations, if any exist, might observe them directly. They may look back at the Fermi Bubbles the way we look back at ancient geological formations on Earth, evidence of previous episodes in a much longer story. After exploring their discovery, their structure, their possible origins, their magnetic framework, and their implications for the future, we can return to the original mystery itself. What do these enormous invisible structures ultimately reveal about the galaxy we call home? There is something strangely comforting about looking up at the night sky. Human beings have been doing it for as long as there have been human beings. Long before telescopes, long before astronomy, long before anyone understood what stars actually were. People looked upward. They saw points of light scattered across darkness. They saw the pale band of the Milky Way stretching overhead. And like every generation that came before them, they tried to make sense of it. Some imagine rivers in the sky, some imagine roads connecting worlds, some imagine the homes of gods and spirits, others simply wondered what those lights were, wondered how far away they might be, wondered whether anyone else was looking back. Today we know far more than our ancestors ever could have imagined. We know the Milky Way is a galaxy containing hundreds of billions of stars. We know our Sun is merely one among those countless stars. We know black holes exist. We know galaxies evolve. We know the universe is vastly larger than anyone once believed. And yet, Despite all that knowledge, discoveries like the Fermi Bubbles remind us that the cosmos still has an impressive ability to surprise us. In many ways, that may be the most important lesson of this entire story. Not that the bubbles exist, not even that they are enormous, but that something so large remained hidden for so long. Think about what we've learned. The bubbles stretch roughly 25,000 light-years above and below the centre of the Milky Way. Together they span about 50,000 light-years. They contain energetic particles. They contain hot plasma. They interact with magnetic fields. They preserve evidence of an event that may have occurred millions of years ago. And throughout all of human history, nobody knew they existed. Ancient astronomers never saw them. Galileo never saw them. Newton never saw them. Einstein never saw them. Not because the bubbles were absent. Not because they were small. Not because they were difficult to reach. They were hidden because the universe was speaking in a language we had not yet learned to understand. The gamma rays were there. The signals were there. The clues were there. We simply lacked the tools to interpret them. There is a certain humility in that realization. Every generation tends to believe it understands reality reasonably well. Then new instruments appear, new observations arrive, and the universe reveals another layer. The story of the Fermi Bubbles fits perfectly into that tradition. A reminder that knowledge is always incomplete. A reminder that discovery is never finished. A reminder that even our own galaxy continues holding secrets. When astronomers first identified the bubbles in 2010, they immediately faced a mystery. What could create structures of such astonishing size? Over the years, several possibilities emerged. The most famous involves Sagittarius A star, the supermassive black hole lurking at the centre of the Milky Way. Today it appears relatively quiet, almost sleepy, yet the bubbles hint that its past may have been far more dramatic. Perhaps millions of years ago gas fell inward, the black hole fed, energy surged outward. The resulting outflow inflated the enormous structures we see today. It is a compelling idea. A black hole awakening briefly before returning to its present calm state. Yet another possibility remains equally fascinating. Perhaps the bubbles are the cumulative result of countless stars living fast and dying violently. Massive stars, powerful stellar winds, millions of years of supernova explosions. Energy gradually accumulating until it carved giant structures into the galactic halo. That explanation carries its own appeal. Not one dramatic event, but many. Not one source, but countless sources working together. And perhaps the truth lies somewhere between those possibilities. The universe rarely feels obligated to choose only one mechanism. Black holes influence galaxies. Stars influence galaxies. Gas influences galaxies. Magnetic fields influence galaxies. Reality often emerges from the interaction of many processes operating simultaneously. The Fermi Bubbles may represent precisely that kind of complexity. A structure born from the combined behaviour of an entire galactic ecosystem. What makes the bubbles especially interesting is that they force us to think differently about the Milky Way. For much of history, the galaxy seemed static. The stars appeared fixed. The overall structure seemed permanent. Even after astronomy revealed that galaxies evolve, it remained easy to think of the Milky Way as relatively calm. The bubbles challenge that perception. They reveal a galaxy capable of dramatic change, a galaxy capable of releasing enormous amounts of energy, a galaxy with a history more dynamic than its current appearance suggests. In that sense, the bubbles function almost like a historical document, not written in ink, not carved into stone, written in plasma, written in gamma rays, written across tens of thousands of light years. The universe has preserved evidence of an ancient event, and modern astronomy has learned how to read it. That ability is remarkable when you think about it. Human beings evolved on a small rocky planet orbiting an ordinary star. Our ancestors hunted animals with stone tools. They worried about weather. They worried about food. They worried about surviving the next winter. And yet, over time, those same humans developed mathematics, then physics, then telescopes, then spacecraft. Eventually, we became capable of reconstructing events that occurred millions of years ago near the center of a galaxy. That journey is extraordinary, not because humanity has learned everything. Far from it. The bubbles themselves prove how much remains unknown. The extraordinary part is that we can ask these questions at all. There is another lesson hidden inside this story, one that extends beyond astronomy. The Fermi Bubbles remind us that appearances can be deceptive. The Milky Way looks peaceful, the night sky looks quiet. Nothing about the familiar band of stars suggests giant structures extending tens of thousands of light years into space. Yet they are there, invisible, immense, waiting to be discovered. Nature often works that way. Reality is usually more complicated than first impressions suggest. The visible universe represents only part of the story. Beyond visible light lie radio waves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. Each reveals different aspects of reality. Each uncovers structures hidden from ordinary sight. The bubbles are a perfect example. They exist beyond the limits of human vision. Without specialized instruments, we would never know they were there. That idea naturally leads to an intriguing question. What else remains hidden? History suggests the answer is simple, quite a lot. Every major improvement in observational technology has revealed something unexpected. Radio astronomy revealed new classes of objects. Infrared astronomy revealed hidden stellar nurseries. X-ray astronomy exposed violent cosmic environments. Gamma-ray astronomy uncovered structures like the Fermi Bubbles. Future instruments will almost certainly reveal additional surprises, perhaps new outflows, perhaps new structures in the galactic halo, perhaps entirely new phenomena nobody currently anticipates. The universe has an excellent track record when it comes to exceeding expectations. Another fascinating aspect of the bubbles is their connection to time. Throughout this journey, we have repeatedly encountered events occurring over millions of years. Those timescales can feel abstract, difficult to relate to, yet they offer valuable perspective. Human civilization feels ancient from our viewpoint. Recorded history spans only a few thousand years. The bubbles preserve evidence from millions of years ago. The Milky Way itself is over 13 billion years old. Suddenly, our familiar sense of time begins to stretch. The galaxy has experienced countless changes before humanity appeared. It will experience countless changes after humanity is gone. Stars will form. Stars will die. Black holes will feed. Galaxies will merge. The universe will continue evolving. The bubbles remind us that we occupy only a brief moment within that larger story. Far from making humanity insignificant, I think that realization makes our curiosity even more remarkable. The universe is enormous, our lifetimes are short, and yet we spend those lifetimes trying to understand it. We build observatories, we launch spacecraft, we ask questions, we investigate mysteries. The discovery of the Fermi Bubbles is one example among many. A species living on a small planet notices invisible structures extending across 50,000 light-years and decides to figure out how they formed. There is something wonderfully human about that. The bubbles also encourage us to think about the Milky Way, not as a static object, but as a process. Galaxies are often presented as things. Photographs reinforce that impression. We see beautiful spiral shapes and imagine permanence. Reality is much more dynamic. Galaxies are constantly changing. Gas flows inward, gas flows outward. Stars are born, stars explode. Magnetic fields evolve. Energy moves through enormous regions of space. The Milky Way today is not the same Milky Way that existed 10 million years ago, nor will it be the same Milky Way 10 million years from now. The bubbles are evidence of that ongoing evolution. They represent a snapshot within a much longer sequence of events. Perhaps that is why I find the phrase, the invisible breath of a galaxy, so fitting. Not because galaxies literally breathe, they do not, but because the bubbles reveal movement, energy flowing outward, material interacting with surrounding space, a galaxy influencing its environment, a galaxy leaving traces of its activity far beyond the visible disk. In a sense, the structures resemble an exhalation, evidence that something happened deep within the galactic core, evidence that energy travelled outward and left its mark on the surrounding universe. Millions of years later, the mark remains. And we happen to be living at the precise moment when technology has finally become capable of detecting it. That timing feels almost unbelievable. For billions of years, the bubbles existed unnoticed. For billions of years, the galaxy carried this hidden history. Then, within a few decades, humanity developed the necessary instruments, and suddenly the structures emerged from the darkness. A mystery hidden in plain sight. A discovery waiting for the right moment. As we reach the end of this journey, it is worth returning to the original question. Why are there bubbles surrounding our galaxy? The honest answer is that we're still working on it. The evidence points toward ancient activity near the galactic centre. Perhaps a feeding episode involving Sagittarius A star. Perhaps intense star formation. Perhaps a combination of both. Astronomers continue investigating. Observations continue improving. The story is still being written, and that may be the most satisfying ending possible. Not certainty, curiosity, not a closed case. An open invitation to keep exploring, because somewhere above and below the Milky Way, extending tens of thousands of light years into space, two giant invisible structures continue carrying clues from the galaxy's past. Silent, enormous, hidden from ordinary sight, waiting for future astronomers to uncover even more of their secrets. And as the night sky continues turning overhead, and the stars continue their slow journeys through the galaxy, the Fermi Bubbles remain there as well. A reminder that even the place we call home is far stranger, far larger, and far more interesting than it first appears.